Yeah, I'll start with that. See how, is it Google? PowerPoint? I think.
Okay. Hello, everyone. Please start sitting down. We're going to start our first afternoon session that is going to be about single source studies. And the first talk of this session is going to be an invited talk by Kenzie Nimo.
Okay, can everyone hear me? Yeah, okay. Can everyone hear me online?
Yes.
Yes.
Okay, perfect. Yeah, hi everyone. I'm Kenzie Nimo. I'm a postdoc at MIT. I'd like to thank the organizers for inviting me to give this talk. And hopefully I'll give you an overview of the observational signatures of emission mechanisms for fast radio bursts. So I'll start with the big questions that I think about and lots of people in this room think about. Of course, there's the mystery about what kind of objects produce FRBs, and then also what the underlying physical processes are responsible for FRBs. And we heard great overview talks both today and yesterday on these topics. There's a wealth of information in the radio properties themselves of FRBs that hold information about both of these big questions. And we see a huge diversity in their radio properties, from their spectral properties, their temporal properties, their polarization properties. And the big question in my mind is this a reflection of progenitors? Is this a reflection of the emission physics? Or is it a reflection of the immediate environments? Or most likely some confusing, complicated picture of all of these mixed together. So to try and understand the emission physics part of this puzzle, let's think about what's broadly true in terms of FRB properties. So here I'm showing the transient phase space. We've seen this in a few talks already. Luminosity on the y-axis and duration on the x-axis. We can see that FRBs, which are in blue, they're coherent, so they have very high brightness temperatures. They are short duration, typically around millisecond timescales, and they're highly luminous, kind of 10 to the 32 ergs per second per hertz on this plot. They're also exclusively in radio, excluding the SGR 1935 burst, of course, and they've been seen from 110 megahertz all the way up to 8 gigahertz so far. And then finally, they're typically highly polarized. These are some bursts from R1, which we heard a nice overview of this morning. And yeah, they're kind of 100% linearly polarized across these bursts. So from these kind of broadly true properties arises the broad categories of FRB emission mechanisms. So I've put them into two classes here. You have processes that occur within the magnetosphere of a compact object. And then you have processes which happen further out. So the central object releases energy in the form of a shock, and that propagates really far out and produces the FRB at much larger distances. Of course, the picture is not quite this simple. We heard from Naveen yesterday that there's a lot of complicated models that fall under these categories. But for the purposes of this talk, I'm going to keep it really high level so that hopefully we can kind of go in one direction or the other. So in the question of are FRBs coming from a magnetospheric emission process or a non-magnetospheric emission process, I'm going to talk about these FRB properties that I've listed in the table. So we're going to look at their spectral behavior, their temporal variability, their polarization angle behavior, their circular polarization, and their scintillation. So starting with the spectral behavior, we've seen plots like this in a variety of talks already. FRBs can be broadband, but they can also be narrowband. And in Ziggy's paper, and then also in this the catalog 2 sample that we just heard about, there is a discrepancy between repeaters and non-repeaters in terms of their spectral properties. So repeaters tend to be more narrowband than non-repeaters. Is this because the repeaters and non-repeaters are different progenitors or different emission mechanisms? I don't know who has the badge that says that, but it's not me. There's also a suggestion that potentially this is a beaming effect, and that it's not due to differences in progenitors or emission mechanism. And then also for repeaters, we see the sad trombone effect, or this downward drifting structure. This is R1. We saw these plots this morning from Jason, where you have these islands of emission that drift from high frequencies to low frequencies as a function of time. So are these properties, can we use these properties to distinguish between magnetospheric and non-magnetospheric models? Unfortunately, not. This behavior can be explained in both classes of models. This Metzger et al. 2022 paper that I cite here is a toy model of a narrowly peaked SED that is independent of the emission mechanism. So some physical realizations of this could be that in a magnetosphere, you could have radius to frequency mapping. So the emission site moves further out as a function of time to explain this behavior. And then for non-magnetospheric models, you could let the shock decelerate as a function of time, and that could also reproduce these results. But what about the timescales? So I said earlier, FRBs are milliseconds in duration. Well, we actually see a huge range of timescales in FRB emission, from 60 nanoseconds all the way up to second timescales. So there's really orders of magnitude difference here. Let's focus on the shortest timescales that we've seen so far, so 60 nanoseconds. If you just do a simple light travel time argument, you get to about 20 meters in emission radius from the 60 nanoseconds, so very, very small. And these small emission sizes are naturally explained in the magnetospheric models, so there's no problem here. However, that was excluding relativistic effects. If we take relativistic effects into account, there's this relationship here between the variability time, the emission radius, and the Lorentz factor gamma. And so you can see if you just bump up your Lorentz factor, then you can let your emission radius get larger. However, for the non-magnetospheric models, there is a similar relation between the width, the total width, and the emission radius. So not the variability time, but the total width. And so if you combine these two equations that have the same dependence on the Lorentz factor, then you basically say that the width has to be roughly equal to the variability time, which observationally is not true. We see orders of magnitude difference between the shortest time scales and the broader envelope in this repeating FB and also in other sources as well. So this definitely adds challenges to the non-magnetospheric models. However, there is a caveat that we did hear about yesterday in Naveen's talk, that if you introduce nonlinear propagation effects, then you can explain this variability in the shock models. So the idea here is you have the burst that's propagating through this plasma, and it gets split up into pancakes, or they're referred to in this Sabachi et al. 2021 paper. And that introduces intensity modulations on a time scale that's equivalent to the radial width, like the size of these pancakes. And the prediction there is that you can kind of get into the microsecond regime timescale variability with this method. So yeah, all that to say that the short timescales and the variability are very strongly supported by the magnetospheric models. They point a little bit away from the non-magnetospheric models, but it's not really a slam dunk, can't be non-magnetospheric models. Okay, so what about polarization? Here I'm showing a plot of the polarization angles as a function of time for the first baseband catalog from CHIME. In the top panel, these are polarization angles that are flat as a function of time for a single component. And you can see that 50 out of the 88 FRBs in the sample exhibit this property. And then in the third panel, that's flat polarization angle across multiple components. And you can see that there's 19 out of 88 that fit that description. And so a significant number of these 88 FRBs exhibit flat polarization angles across time. However, we do sometimes see jumps in the polarization angle, and even we've seen swings in the polarization angle. So changes in the polarization angle can be explained in magnetospheric models. We see this in pulsar emission. In the non-magnetospheric models, these jumps and even some smoothly varying polarization angles can be explained. However, in the case of this PA swing FRB, the polarization angle swing is well fit by the rotating vector model that we see for pulsars. And that is really hard to explain without the interpretation of having a beam of light that's sweeping across your line of sight, like a pulsar, and therefore tying this emission to the rotation of the object, i.e. the emission must be coming from within the magnetosphere of this object. And so this swing points away from the non-magnetospheric models for this FRB. Furthermore, I did say that FRBs are typically highly polarized. Specifically, they're typically highly linearly polarized. You can see in this plot, this is a polarization study of the DSA sample of FRBs, where most of the FRBs are very high linear polarization and little to no circular polarization. Again, sometimes we see circular polarization, and in the literature, it's been reported up to 90% circular, so very high circular fractions. These circular polarization measurements are consistent with magnetospheric models. There's an interpretation that if you're looking at the emission straight down the beam of the emission of the burst, then you will see 100% linear. But as soon as you start to go a little bit off axis, then you'll start to see significant circular polarization. The same interpretation is true for non-magnetospheric models. However, the expectation is that the flux will significantly drop as you go more off axis. And at the moment, there's no obvious correlation between the flux of bursts and their circular polarization fractions. But furthermore, the prediction really is that the flux will drop so much that you won't even see it at cosmological distances. So that challenges this interpretation for the non-magnetospheric models. However, propagation effects can be introduced to explain significant circular. So there's things like Faraday conversion, where you would get significant circular fractions from propagating through that plasma. And so I have marked this one more as a question mark, since it's not naturally explained in the non-magnetospheric models. However, propagation effects can explain this behavior. Okay, the last property that I want to talk about is scintillation. So if people were at the November meeting, I presented on this result. So I'm not going to go into too much detail, but I'm happy to chat offline if people are interested. What I'm showing here is an autocorrelation function of an FRB spectrum. So we take the intensity as a function of frequency, we autocorrelate it. And in this autocorrelation function, we see two clear Lorentzians. and Lorentzians are the expected functional form for scintillation. And in this work, we interpret these scintillation scales, one being from a plasma screen within the Milky Way, and the other from a plasma screen in the FRB's host galaxy. As we heard from Rob yesterday in a great overview talk, when you have two scintillation scales or scintillation and scattering measurements, you can use that the coherence of scintillation to place a constraint on where those screens are, but also to use it to put a constraint on the size of the emission region. The analogy that Rob made and that I'll also bring up is stars and planets. So stars, they twinkle because of scintillation from Earth's atmosphere. This is because they're far enough away that they're a point source with respect to the diffractive scale of Earth's atmosphere, whereas planets are closer, and so they appear larger, they're spatially resolved, and you lose that coherence and you don't see scintillation anymore. The same is true for FRB emission. If we have this plasma screen in the host galaxy, then we know that the FRB site has to be a point source-like with respect to that screen. And so you can use that logic to place a constraint on the size of the emission region. And in this case, we were able to place an upper limit of 3 × 10⁴ kilometers on this emission radius. Again, like I mentioned, for the temporal properties, really small emission region sizes are naturally explained in the magnetospheric models, where you expect really small emission regions. And for the non-magnetospheric models, you kind of expect 10⁵ kilometers and higher, so with the upper limit that we place. And so this measurement of the emission size, this constraint on the emission size, disfavors the non-magnetospheric models for this FRB. So as you can see from this table, there is growing support for the magnetospheric models in the studies that I've presented. And there's some challenges to the non-magnetospheric models with caveats that just are not so naturally explained, that can't naturally explain the emission properties that I've mentioned here. However, I don't think that that's kind of the end of the story. I actually think that there is evidence for multiple emission mechanisms. I'm showing 2 bursts here from 2 different repeating FRBs. And they're showing very similar morphological structure. So you have these kind of sharp components on top of a broad, drifty envelope. You have some wider components that look like maybe they're changing in their dispersion measure or maybe changing their drifting properties. And in this Hewitt et al. 2023 paper, the analogy is drawn to solar flares. And I think Jason also mentioned it earlier today, where in solar flare emission, you can get these kind of sharp structures that are thought to come from magnetic reconnection happening near the solar surface. And the broad drifty components are thought to come from shocks that propagate out into the corona. So quite analogous to our magnetospheric and non-magnetospheric models. Of course, solar flares are at totally different energies, frequencies, timescales, but at least morphologically, the analogy is there. And then moreover, there's this growing evidence that repeating FRBs exhibit this break in the energy distribution. I'll refer to Omar's presentation following me, who I think will go into a little bit more detail on this. But when I see these, I think, is the emission physics for these low energy bursts the same as those in the high energy tail, or do we have different physical processes driving these different distributions? And I think to tie back to the scintillation result, which I think is a really powerful tool in understanding the emission physics, it would be really great if we could explore if the scintillation properties in these low energy bursts compared to the high energy bursts differ, pointing towards different emission radiuses or emission processes. Okay, so to summarize, we have this diversity in radio properties that potentially indicates a mess of progenitors and emission processes and immediate environments that are all confused together. But we are working to disentangle this actively. So I only talked about emission processes, but of course we've heard many great talks on looking at the host galaxies and local environments of FRBs, which tells us about their progenitors. And I'll highlight again, I think it's been in every talk at this point, but I'll highlight again the recent CHIME FRB outrigger localization of a non-repeating FRB and refer to Mawson's talk later on in the week. For the immediate environments, Rob gave a great overview of the different propagation effects that we can see in FRBs, and that gives us a wealth of information of about the plasmas that the FRB propagates through on its way to Earth. And I wanted to highlight this cool result that I thought was interesting of a repeating FRB study by FAST, where they see that the rotation measures pretty flat with time for a very long time, and then out of nowhere it flares and jumps up by over an order of magnitude in the RM. And the interpretation there is that that there's this magnetized flare of plasma potentially from a companion, a binary companion, driving this RM behavior. And then, of course, the emission processes. We have a lot of interesting observables in the FRB population, and they are pointing towards a magnetospheric model in these cases. The big caveat is the session title, single sources. Basically, everything I talk about are kind of individual sources or small sample studies. And so it's very unclear whether or not this table is really reflective of the entire population or whether we've just been able to do these really detailed studies on individual weird FRBs that don't really reflect the broader population. And so, yeah, I'm really interested in scaling up these efforts. CHIME has thousands of FRBs, so we should be able to scale up all of these observables and really explore the emission physics broadly for the FRB population. Thank you, and I'll take any questions.
Thanks, Kenzie, for keeping to the time and for an amazing talk. Do we have any questions? Okay, there's one online. So do we have the catch box? Okay, yeah.
Yeah, so we have a question online in the chat that says, can the non-existence of sad trombone drifts at high frequencies above 4 gigahertz provide evidence that the frequency time structure is strongly coupled to propagation effects and not as much to the emission geometry?
That's a good question. So I think broadly, we don't really understand the like the drift rate of the sad trombone effect. So it's possible that there's some frequency dependence on the drift rate, that it could be slower at high frequencies, and therefore you wouldn't see it observationally. I guess the one argument against it being a propagation effect that I've heard is that for plasma lensing, you would expect it to go equally downward drifting and upward drifting. And we typically see it downward drifting, and very rarely do we see upward drifting structure. And so I think that data point at least pushes it away from a propagation effect. But the frequency dependence of this and the driftiness of them is, I would say, not well studied.
Cool. Other questions over there? We could send the catch book.
Hi, Martin Topinka from Cagliari. I wanted to ask about the Lorentz factor. You mentioned what are the typical values? They're like assumed, or is there any way how to directly observe for a particular FRB the Lorentz factor somehow using the particular model?
Yeah, I think the Lorentz factor is very unconstrained. I've seen numbers kind of in the hundreds, thousands, maybe higher, reported in the literature, not measurements, but from models. In terms of measuring or constraining the Lorentz factor, I think if we could have if we could take like temporal variability as a constraint on the emission size, as well as the scintillation simultaneously, you could probably combine those measurements or those constraints to place a constraint on the Lorentz factor. If we could see it in the same burst, potentially.
Okay, I think there was another question in the room. Yeah.
Hi, this is Laura Spitler. So I have a question. You mentioned you talked about the polarization position angle, either flat or swings within a single burst. I'm curious if you take that and then you have multiple bursts from a repeater on, say, like a time scale of an hour. Can you comment on how constraining, say, them all having the same PA over the hour versus like PAs jumping from burst to burst is in constraining one of these two origins?
I think it's not constraining because I know that the both models can have different polarization angles for independent bursts. The variation, the interpretation of the variation, the PA swing is rotation. So unless the repeat bursts are kind of within the rotation of the object and you're seeing essentially like discrete patches of the RVM, then I think it wouldn't distinguish between magnetospheric and non-magnetospheric models. However, I know like polarization behavior in repeaters, there's like proposals that you could use it to constrain like a precessing neutron star. Like in the case of R3, for example, you could use the PA behavior to discuss between like a binary model or a precessing neutron star. So there's maybe like bigger picture questions, like progenitor questions you could answer. I'm not sure on the emission physics.
Okay, we have time for one last question. Yeah.
Oh, okay. So, it's my turn. Okay. Hi. So, I just can you hear me?
Yes.
Oh, okay. So I just want to add two very quick points. So for the spectrum behavior, actually the shock model also cannot explain, I mean, the narrow spectrum. So if you use the relative bandwidth delta nu over nu, you will see many repeating FRBs have the typical value from 0.1 to 0.3. But if you have a very large shock structure due to the high latitude effect, this will cause the delta nu over nu much greater than the observed values. And another thing is, so you mentioned the nonlinear propagation effect, the filamentation instability. Roughly at 3 years ago, there's a paper by Wenbin, Pat Binyamini, and Pawan Kumar. They calculate in order to satisfy the observed variability time scale, actually the growth rate of the filamentation instability is very low. So maybe it still cannot explain why we see so small variability time scale. Okay.
Yeah. Yeah, I appreciate your comments. I think on the topic of the narrow bandedness, like I referred to the Metzger et al. 2022 toy model, which has a few physical realizations. So it's not broadly applicable to all non-magnetospheric models, but there are instances in which you can explain the narrow bandedness. And then for the temporal variability, I agree with you, and I've read the Benyamini and Kumar paper. I think the timescales still are maybe a little bit off, but it does in terms of the these nonlinear effects kind of are in the kind of tens of microseconds regime, and we've seen down to 60 nanoseconds. So there's still quite a jump in those timescales that is unexplained from these nonlinear effects, but it does make me a little bit concerned about the I guess slam dunk ness of temporal variability for magnetospheric versus non-magnetospheric. But I mean, Naveen's talk yesterday highlighted nonlinear effects and kind of highlighted that more studies on these kind of propagation effects are really needed to understand this better.
Okay, thanks.
Thank you.
We can chat.
Okay, if
Yeah.
you have any more questions, could you please ask them on Slack or during the coffee break? And let's thank our speaker again. Okay, our next speaker is Omar Ould-Bukatin, who will talk about apparent DM and RM changes from a repeating FRB source.
Thank you. Can everybody hear me clear? Great. Apparent dispersion measure and rotation measure changes from a repeating fast radio burst source. My name is Omar Ould-Bukatin. I'm a PhD candidate in the AstroFlash team, which is hosted here at McGill, at Astron, and the University of Amsterdam. I'm happy here to speak to you at FRB 2025. And we all have a common goal. We all try and get a little bit closer into answering the question, where are FRBs coming from? Why are they happening, etc. And I think in order to study these things, we have to really zoom into the local environment. And you can do this, study the local environment using propagation effects, as we heard yesterday. And you can do this for one-off sources, for which we'll hear more about later this week. But if you want to study time variability in propagation effects, then you would need naturally a repeating source. But studying, so two of the most studied propagation effects, or the most profound propagation effects, are dispersion and rotation measure. But finding and claiming variability on these two properties is non-trivial and requires great data, but also a special source in that sense. And I do my observations using an array of telescopes located in Europe. They're rather small, 25 to 32 meters. It's the Westerbork telescope in the Netherlands, the Onsala telescope in Sweden, the Stocker telescope in Germany, the Dwingelo telescopes in the Netherlands, and the 32-meter Torun telescope located in Poland. We do not work interferometrically, but individually at complementary wavelengths, and we observe as much as we can. So to give you an indication, last year with Westerbork, I conducted more than 6,500 hours of follow-up studies for repeating sources. Of that, like 1/1,000,000% is like actual data, but quite a lot of hours. Collectively, we call ourselves Hyperflash, and our aim is to do high cadence monitoring to observe the brightest and therefore also the rarest FRBs. We have another high cadence monitoring program within the AstroFlash team in Europe, which is the ECLA initiative, making use of the Nancy radio telescopes, which is this giant wall, but it's equivalently sensitive to a 100-meter telescope. Its PI is Dante Hewitt, and it's supported by Sylvain Ranguin and Jeff Huang. So now that we know our telescopes, we need a source. So I was very happy that in the middle of 2024, the Meertrap team released an ATEL by Tian et al. On FRB 2024-06-19D. And after the release of this ATEL, it took us 13 hours to be on source, and we conducted a high cadence monitoring campaign. A week later, we released our own ATEL on the bright detection of a single FRB. This is using a 25-meter telescope in Europe, and when coherently correct for the dispersion measure, we exceed the signal-to-noise of over 1200. So it's basically a delta function. It is close to 1,000 Jansky milliseconds, and I think it's one of the highlights for the Westerbork sample. In total, we observed for more than 500 hours in 4 months and achieved more than 200 detections. I want to highlight here that this wouldn't have been possible without the release of the ATEL. Astronomers' telegrams, for me as follow-up researcher, are extremely important. So whenever I make a detection or find a reactivation of an FRB, I try to communicate that via the ATEL. So VO events and the astronomer telegram are vital to do the follow-up monitoring. Another detection I would like to highlight is the detection we did with the Dwingelo telescope, which in 1956 was the largest radio telescope in the world. But is now being repurposed such that we can also try and detect fast radio bursts with it. The reason why Max is on this slide is you have to be physically present in the dish in order to do observations. Unluckily for Max, the source was only visible between 3 and 5 a.m. during the times of the ATEL, but he spent nights there, and not without any success, he detected this very bright FRB. And as you can see on the top panel, I quote intensity, because in order to quote signal to noise, you would need noise. There is no noise because everything is RFI, because the telescope is located next to the headquarters of Astron, and there's all types of RFI environments. So it's just signal, but there is an FRB there. So now let's look at the collective properties of all the detections which we have, the cumulative burst energy distribution. On the y-axis, we have rate, the amount of burst you can expect per hour above a certain energy. And on the x-axis, we have fluence in Jansky milliseconds. So now let's just add all the bursts. And we find that the energy distribution breaks towards higher energies. This is not the first time you've heard this. If you paid attention in last talk by Kenzie, you saw other examples. But I also mentioned this at other conferences in the last years, and I'm very happy that you all remembered it. But I'll put them up. For FRB 2020 1124A and 2022 0912A, we find a similar behavior where the energy distribution breaks towards higher energies. I want to emphasize that this is only possible due to high cadence monitoring, so making use of hyperflash in this case. You could see basically the left side of the energy distribution. If you have a sensitive telescope, you detect all the weaker bursts. And on the right side, you do not need a more sensitive telescope to detect these bursts. You just need time. I have lots of time. So therefore, we can try and detect these bursts. And I see you wondering, there's this odd circle there. That shows it indicates that perhaps the Nancy radio telescope could also detect that break, but due to the observing hours, we were not able to probe the high energy tail only using the Nancy sample. But it is a very bright FRB, close to 1,000 Jansky milliseconds, with a telescope which is roughly 100 meters. So how would the dynamic spectrum look like? That's this. It's the same burst that was detected by Westerbork. At the bottom, I show the waterfall. We use waterfall plot. We show a custom color scale because otherwise you wouldn't see anything because it's so incredibly bright. In the middle, I show the time series using the polarimetric properties. We plot this in log scale because the signal to noise exceeds over 6,000. So we do need log scale here. And at the top, I show the PPA, which is relatively flat and is comparable with the results found in the discovery paper by Tian et al. Notice that the DM, it has been corrected for dispersion and all the smaller components all align with this main dispersion. So we're able to measure the polarimetric properties for the burst sample for the Nancy radio telescope. So what we did for the 5 epochs for which we had detections, we took the 2 brightest detections of each day and measured its rotation measure over time, which I show on the following plot. So here on the right, I show rotation measure plotted over time, and we find that it isn't constant. It's changing over time, roughly 100 radians per square meter in a month. So that's the first time variable propagation effect. Now let's look at the sample detected by Westerbork. Here I plot them all at the same time and frequency resolution, so it's easy for you to spot the differences. The first one that I see, and I also want to highlight, is the fact that the temporal range is quite broad. For one burst, I show 5 milliseconds. On the other, I show 50. So there's quite a range, again, for this sample. But as you can also see, there are also unresolved components to these bursts. Luckily, at Westerbork, we record with baseband mode, which means it's a pitfall. You can do all the time resolutions which you like, but we can go to higher time resolutions. So now let's take the brightest burst here, which exceeds the signal to noise, comes close to that 1300, and look at that at 1 microsecond, when it's still signal to noise 450. I plotted at minus and plus 0.1 parsecs per cubic centimeter to indicate that the middle is the actual correct DM. And you can do this over a trial of DMs, right? And then take the peak signal to noise, create a curve, and assuming that it is completely straight in a single component, you can very accurately determine the dispersion measure. So we did that. And we find that this is the most accurate dispersion measure for this burst. Now let's take it for a burst detected a week later. Every step we take here in dispersion versus signal to noise is coherently done. So this is a week later, 1 microsecond. We take a burst detected another week later. As you notice, in the signal to noise versus DM column, the x-axis is shared, indicating that the dispersion measure is evolving over time. So let's take the 5 measurements for which we have can accurately determine the dispersion measure, and we find that it is increasing over time. A total of 0.4 units in roughly 2 months. We did it. Time variable propagation effects. What can you do with it? This is great. Now we have post stamps. We have stamps. We collected them. It's great. What do we do with it? As you probably all paid attention yesterday, we can now try and calculate the parallel magnetic field strength. And we did that, and we found it to be 0.3 with an error of 0.2 milligauss. The large error comes from the errors which we have on the rotation measure. And the first time that we calculated this, I was like, great. What does 0.3 milligauss mean? So you go back where you always start, the fundamentals, the handbook for pulsar astronomy. You turn to page 87, the interstellar medium, and you find that it's roughly a microgauss. So we are already 300 times higher than a microgauss. So let's compare it to a sample of repeating sources. The first one being the first repeater, 2012 11028, where they calculate the parallel magnetic field strength to be between 0.6 and 2.4 milligauss. So that's a factor of 2 to 5. Then there is the FRB 2019-0520b, also known as the R1 twin, by Reshma and Thomas. And there they calculate the parallel magnetic field strength to be between 3 and 6 milligauss, which is an order of magnitude away from what we currently have. The conclusions for both these sources was that it is in a dense magnetic environment. And where we conclude what our sources lie within these two numbers is that it's not in a as dense magnetic environment, but in a relatively dense magnetic environment. And that's the main conclusions. If you have any questions, you would like to discuss this further, you would like to collaborate with Hyperflash, let's chat. I brought stroopwafels. The other members of our team also have access to these stroopwafels. So if you want to ask them questions, that's also possible. We also have katja biffietjes, which are gluten-free variant of the stroopwafels. And I'll leave you with my summary slides. And if you have any questions, I'll be happy to answer them.
Thanks, Omar, for a really nice talk. Do we have any questions from the public? See one there.
Hey, thanks for the really interesting talk. I'm Pavan from Sunil University. This is probably a naive question, but do you see a similar trend when you structure maximize the bursts and instead of doing the SNR maximization for the DM?
For the which?
For the DM evolution.
For which DM? Oh, I'm sorry, I don't understand your question.
Oh, I mean, I think you were mentioning about the SNR maximization for estimation of the DM.
Yeah.
Do you see a similar trend when you structure maximize it rather than just SNR maximizing it?
We are SNR maximizing every burst. That's how we determine we don't do structure optimizing. We just do signal to noise optimizing in that sense.
Right. So do you see a similar trend in evolution of
Oh,
DM?
right. No, we didn't do that because we just do signal to noise optimizing and we don't see any need to do structure optimizing in that sense. Yeah, because we did the old pay trick and this is pretty strict. Like I can't get this DM better for these bursts. Yeah.
Thanks.
Hope that helps.
Katia, behind you.
Oh.
Hi, nice talk. I was just interested in the last date of the last DM estimate you had. So the DM was consistently increasing. So the last day was.
Okay. It's somewhere. Is that what you mean?
Okay. So it was 8th of August. Sorry, 18th of August. Last year. Okay, yeah. Because I also had observations after that.
Mm-hmm.
And the median DM estimates from that showed like the DM was like reverting. So it was like fluctuating. So the median estimate was not secularly increasing, but it was showing this fluctuation.
Yeah, that is varying. Yeah.
Yeah.
What we try and do also in the paper is not interpret this as linear, even though we see 4 points increasing. We try not say it's linear. And when we do the calculation for the parallel magnetic field strength, notice that the overlap where the DM and the RM are actually where we both have the samples at the same time. That's where over that change, that's where we calculate parallel magnetic field strength.
Okay.
So we don't do that for the calculations after 18th of August because we don't have any RM measurements there. Yeah.
Okay, thank you.
There's time for one short question, so maybe the person online can ask, or
Thanks. This is just a clarification question. Is the inferred B this also varying with time? They say they missed this.
Is that also varying with time? Well, if there's another activity period of this source and we find the same variations in DM and RM, then we can try and see if it's consistent or not. But it was just made on the single observation that we have DM and RM changing over time in that sense. Yeah. Yeah. So we can't quote multiple numbers because there's not multiple epochs yet. We just have to be hopeful.
okay, so if there's more questions, please talk to Omar during the coffee break. He has stroke baffles, or you can ask them on Slack as well. So another.
Thank you.
Thank you.
Right.
Yes. Yeah. Okay, so our next speaker is Alexandra Moroyan. Please take it over.
Thank you. Hi everyone, my name is Alex. I'm a PhD student who's part of the AstroFlash team at the University of Amsterdam, co-advised by Jason Hessel, Ziggy Punis, and Benito Marcote. And today I'm going to be talking about our milli-arcsecond EVN localization of the high DM repeating FRB 2019-0417A and its candidate PRS. So as we know, one of the ways we can sort of learn more about what FRB origins may be is through FRB localization. And today, FRB localization is better than ever with new and existing instruments such as the Chime outriggers, ASCAP, Meerkat, DSA 110, just to name a few. Through these, we're able to achieve arcsecond, or in the case of the outriggers, 50 to 100 milli-arcsecond precision for both repeating and non-repeating FRBs. So the number of localized FRBs we have is steadily growing, and it's a very exciting time. That being said, milli-arcsecond precision localization is still important. And by milli-arcsecond in this case, I mean a few milli-arcseconds, to the point where we're able to zoom in on the local environments of FRBs down to parsec scales. And the only way we can achieve this is through very long baseline interferometry, VLBI. And I'm part of the PRECISE project, which uses the EVN to follow up repeating FRBs, usually FRBs first detected by Chime, to zoom in on their local environments. And this has revealed a diversity of FRB environments, but one of the most exciting results that has come out of VLBI observations of FRBs is entering the era of persistent radio sources. So persistent radio sources, or PRSs, as most of us know, are non-thermal luminous sources of persistent radio emission that are compact on VLBI scales and have been found to be coincident with a rare few FRBs, around 3% of localized FRBs. And these FRBs tend to share quite similar properties. I'm going to be focusing on these two, 121102A, the first repeater, or R1, and FRB 2019-0520B, also dubbed the R1 twin due to their similarities. So both of these FRBs are repeaters. They have large and extremely variable rotation measures and generally pretty high DM host contributions, specifically in the case of 2019-0520B. The PRSs, so as I said, they've been found to be spatially coincident with PRSs, and these PRSs have been constrained to sub a few parsecs. They have negative spectral indices in the case of these two sources around negative 0.4, very luminous with luminosities around 10 to the 29 ergs per second per hertz, and they are both in low metallicity star-forming dwarf galaxies. Interestingly, 2024-0114A has also recently been localized to a low metallicity SMC-like satellite galaxy. So it also does share these properties, but this FRB doesn't have as high and variable of a rotation measure, for example. Introducing FRB 2019-0417A. This is a repeating FRB discovered by CHIME in 2019. It's specifically interesting because, as you can see on the graph on the left, the orange histogram is the extragalactic DM contribution or distribution of 40 repeating CHIME FRBs. And this FRB very much sits at the tail with a high DM of around 1,380 parsecs per centimeters cubed. It's also got a high rotation measure of around 4,600 radians per meter squared, though this is slightly lower than R1 and its twin. And it has a candidate PRS identified by Ebic et al. So you can see in the image on the right, the red ellipse is the CHIME localization, and the source S1 is the candidate persistent radio source associated with a dwarf galaxy host at a redshift of around 0.13. So obviously, the localization region of this FRB by CHIME is 1 arc minute in diameter, so we can't definitively say anything about this association. What we did with PRECISE was we observed this source with the EVN during 7 observation epochs from February to August in 2022. During these epochs, we detected 8 bursts, 5 of which had a high enough SNR and didn't show significant ionospheric variations or errors that we used for a EVN localization. So for reference, when we have 1 burst, as you can see in the image on the left from our 2024, we tend to have multiple equally bright peaks when it comes to the localization. This GIF zooms into a 500 by 500 milliarc second region, essentially the same size as the ellipse in the image on the left. And the more bursts we add in, the more of the UV space we sample, we eventually ended up with a localization of this FRB at this nominal position plus or minus 5 milliarc seconds. So we were able to localize this FRB to around the size of the EVN beam. The next question is, did we see a PRS in the continuum data? So we did indeed see a PRS that is still compact on EVN scales. It is consistent with the position quoted in Ebic et al. 2024, has an integrated flux density of around 190 microjanskis, a radioluminosity of around 7 times 10 to the 28 ergs per second per hertz. We have a conservative size constraint of a maximum of 35 parsecs. For reference, the Crab Nebula is around 3.4 parsecs in diameter, so we want to observe this in higher radio frequencies so we can constrain the size further. But overall, properties are consistent with those quoted in Ebic et al. 2024. The next question is, are FRB 2019-0417A and the PRS still spatially coincident? And the answer is very much so, within 10 milliarc seconds, corresponding to a maximum offset of 25 parsecs between the 2 sources. But you can see the FRB dirty map is the background image, and the EVN position of the PRS lies right on top of the FRB localization. So we have officially confirmed another FRB PRS system. What are the properties of this new system? So Dante Hewitt from our team did an RM analysis and found that the RM varied between around 3,900 and 5,000 radians per meter squared. So there is indeed a variable rotation measure, and a new paper on the archive led by Feng et al. Confirms that they also saw this variability. The most probable DM host we derived had a lower limit of around 550 parsecs per centimeters cubed, so an extremely high DM host contribution, and a 3-year DM variability with a maximum of 1 parsec per centimeters cubed. Essentially, we did not observe any DM variability in this source. Again, the PRS has been shown to be compact, had an in-band spectral index of -1.2, very luminous, and in a low metallicity star-forming dwarf galaxy. We also note that its properties, I took this image from the Bruni et al. 2024 paper, but it does lie on the luminosity RM relation that has been quoted in a few papers. So it's consistent with other FRB PRS systems in this regard. What's specifically interesting is now with another confirmed FRB PRS system, we're starting to see that these systems predominantly occur in low metallicity dwarf galaxies. And as we heard from earlier talks, these past 2 days, that's different from the majority of FRBs. So plotted here in green is the host properties of repeating and non-repeating FRBs. In this case, R-band magnitude versus redshift. This was done by Maria Drought and Daisy Ivic. And you can see in color here at the bottom is where FRB PRS systems lie. So they're in lower mass, fainter dwarf galaxies. But what's even more interesting is when you plot the metallicity versus the mass of FRB host galaxies, in green is the majority of FRB hosts, but then FRB PRS systems are located here, and 2024-0114A is also located in the purple square, making their hosts more consistent with those of long gamma ray bursts and superluminous supernovae. So what does this mean? Do these systems imply one or multiple classes of repeaters? This is still an open question, but there's a few possible explanations that could explain why FRB PRS systems have these properties and occur in these host galaxies. One is a continuum scenario. And what I mean by this is PRS FRBs could potentially be the youngest repeaters, or alternatively, and what is probably more likely, is they could be the repeaters that are born in extreme low metallicity environments. So low metallicity dwarf galaxies have less wind. In this case, magnetars could possibly be born with higher spins and dump a lot of dense matter, which would explain the high DMs and high rotation measures that we see. A lot of models, for example, one for magnetar wind nebulas proposed by Rahman et al. In 2025, say that in this case, we would expect the PRS to fade around within 10 to 100 years. So these are very young systems. Alternatively, there's a possibility that they're a unique engine, for example, a massive accreting system, or a separate class of repeaters altogether. One thing that could potentially justify this is it's been shown that black hole mass and galaxy size tend to scale together. So it could be that, you know, these PRSs are explained by a massive accreting system. In this case, we'd expect a long-lived PRS with minimal dispersion measure and luminosity evolution. And potentially we'd expect the rotation measure variability to remain. But both these cases could explain why FRB PRS systems are rare, either because they're quite young or just because they're rare emitters of FRBs. So in overall, FRB 2019-0417A adds to the growing subclass of PRS-associated repeaters. We've officially confirmed another FRB PRS system, and we found that it shares quite similar properties with those of R1 and its twin, though it can be argued that maybe it's a less extreme version and a bridging source between that and FRB PRS systems like 2024-0114A. But we're starting to see a pattern emerge here. For example, the fact that they're all in these low metallicity dwarf galaxies kind of differentiates them from other FRBs, which is interesting. So a lot of additional questions. And that's it. Yeah, I'm happy to take any questions.
Thanks, Alex. Really exciting results. Do we have any questions? Okay, so we have Kavya.
Thank you very much, Alex. So that was a great result. So I was like, sorry if I have missed it already. I was just checking whether you had removed any bursts detected during the observation while imaging and looking for the PRS.
So we didn't remove any bursts, but we do have about 30 hours or so on the PRS in this case. So it wouldn't be expected because none of these bursts were really bright as well. It was all just kind of like SNR of around 9. So we wouldn't expect them to be kind of making a false PRS, if that makes sense in this case. But we will do that to double check.
Thank you.
Okay, we have another question over there. So maybe someone in between.
Hey, Alex, this is Calvin from Berkeley. Great talk. I was wondering if you checked along the line of sight for groups or clusters and what the scattering timescale of this burst is. The DM excess and the 35 parsec transverse size seems to imply very high electron density in the local environment.
So there's a few things that we're still finalizing. A lot of it is in prep. So I can't give you an exact answer on the scattering timescale. But regarding checking for clusters in the line of sight, we haven't seen any obvious ones. I still need to do this, but we are currently doing a bit of a simulation when I said that there's a lower limit of around 550 of DM host. This was assuming a kind of optimistic or conservative DM halos contribution. But right now we know that to explain the sort of excess DM, we would expect an intervening halos contribution of around 800. So we're trying to figure out like what scenario of intervening halos we would need to explain that away. And one of the ways we'll do that is by looking at archival data to see if we see evidence of a cluster. But right now, just from the preliminary results, we haven't.
Sounds good. Thank you.
Do we have another short question? And if not, you can ask Alex during the coffee break again. Let's thank her again.
Was this yours?
Yeah.
Okay. Take a second.
Hello, I think.
Okay. Our next speaker is Kavya Shadji, who will talk about long-term observations of FRB 2024-0619D and R1.
Yeah. So, good afternoon, everyone. I'm Kavya Shadji, and I'm a second-year PhD student at University of Sydney. So I'm giving this talk on behalf of the entire METRAP collaboration, and I'll be discussing some of our interesting results from long-term monitoring of two repeating FRBs. The first METRAP repeater, FRB 2024-0619D, and the well-studied first repeater, FRB 121102A, also called as R1. So thanks to Kaustubh and Ben, who gave like a detailed overview of the METRAP backend in transient searches. So METRAP discovered FRB 2024-0619D on last year, June, and it was initially discovered with a signal-to-noise maximizing DM of 486. And the source was localized using the transient buffer voltage data, achieving a positional uncertainty less than 1 arcseconds. And we find no significant optical counterpart in any of the archival images. And subsequent detections from GMRT, Westerbork, and also Meerkat confirms the source's hyperactivity as discussed by in Omar's talk. So hyperactive repeaters are characterized by their exceptionally high burst rate, often emitting tens to hundreds of bursts per hour, which is like significantly exceeding the activity levels of typical repeating FRBs. And follow-up observations of hyperactive repeating FRBs have been extremely successful in revealing many of the properties such as like spectral as well as temporal evolution of the burst activity and burst properties, which are very valuable in constraining the different emission mechanisms and progenitor models. So we have been following up this source with Parkes or Muriang telescope, Meerkat, Lovell, and Atka. We were having high cadence and long-term observation. So in the first session of my talk, I'll be discussing the results from that high cadence monitoring. So our observation revealed an extremely high burst rate with a total of 1,500 bursts detected with Meerkat, Lovell, and Muriang, spanning a frequency range from 0.5 to 4 gigahertz. Muriang alone detected nearly 1,100 bursts, benefiting its wide bandwidth and sensitivity. So in the first plot, I show the burst rate variation with the time and frequency. So the filled markers indicates the detections and unfilled markers indicate non-detections with a 95% confidence Poisson error bars on them. So the source was active until 4th of September, after which we did not detect any further bursts, but the long-term monitoring is still going on. So what stands out is the source is exhibiting like clustering in like a temporal clustering in its activity. So we found an estimated 350 bursts per hour in early August. Then we found a sharp decline in the burst activity. So, and the figure on the right side shows this scatter plot of the bandwidth, measured bandwidth and width distribution of the burst. So nearly 40% of the bursts detected are very narrow banded, having bandwidth less than 100 megahertz. Also, we find strong frequency dependence in the emission. Again, 40% of the total detected bursts are detected between 1.4 to 1.7 gigahertz. Such a frequency-dependent emission is also seen in other repeaters such as R1 and R2. Again, taken together, confirming that such a frequency-dependent emission could be something intrinsic to repeating FRBs, unlikely to be solely due to propagation effects. So here I just show a subset of the bursts detected from Montréal. And detailed analysis of such a spectrotemporal polarimetric properties of the burst from the source detected with MeerKAT has already been analyzed and published by June Tian this year. So here I just discussed the results from Montréal. So out of the total detected 1100 bursts, 80 bursts detected resulted in a measurable RM. And we find that most of the bursts are linearly polarized, nearly 97% of them. And 3 bursts exhibit significant circular polarization. And this occasional circular polarization and high linear polarization again support magnetospheric origin processes. Also, we find modest variation in the polarization angle in 17 of the total 80 bursts. Also, 24 of the bursts are microseconds in hundreds of microseconds in duration, but they are resolution limited, indicating they can be even narrow in time or can consist of unresolved substructures, again supporting compact and coherent emission regions. So here I just show the RM evolution of the source. So as discussed by Omar in his talk, I haven't tried to check a correlated evolution in DM and RM within a single day, but that would be something great to do. So here I just show the median estimates of the RM as a fitted trend line. So we find that the magnitude of the RM is increasing at a rate of 1.85 rad per meter square per day. And so I think I have got the signs wrong here. And we find that the DM of the source is not evolving because nearly in the start of the September, we found that the DM value again went back to around 464. So we find that there is no correlated evolution in the DM values, but up to a limit of 1 to 2 parsec per cubic centimeter, which is also, again, something to be investigated. So several repeating FRBs such as 1903-03A and also 1809-16B. Here also, I think I got a sign wrong. The RM is increasing in the case of, here the RM is increasing in the case of 1903-03A, and they don't have any correlated evolution in the DM. It might actually indicates that the DM and RM are arising from different regions around the progenitor, or the Faraday rotation evolution is solely contributed by evolution in the magnetic fields. Also, we looked for a periodicity in the burst arrival times. So we just simply ran a Lomskagel periodogram, and we find no periodicity in the burst arrival times, but robust analysis on the periodicity is also yet to be undertaken. And the wait time distribution of the burst is also analyzed. So this plot shows the density plots of the wait time distribution with the observed data compared with a Weibull fit. So we find that the Weibull distribution with a shape parameter value less than 1 is actually giving a reasonable fit to the observed wait time distribution, indicating clustering in the burst arrival times. So repeaters like R1 and R2 is also shown to exhibit such a clustering in activity, which is also something to be done with the emission mechanism. Also, we searched for the presence of a PRS near the source with spanning a frequency range from 0.5 to 12 gigahertz with MeerKAT and ATCA. So here I just show the continuum images from MeerKAT at L, U, and S bands. So we found no PRS, but only upper limits. But here also I want to make a point that we did image this source after removing the burst detected during the observations. Otherwise, we were seeing a continuous and compact emission near the source. Once we remove the burst, we find there is no continuous emission, and it was solely due to integrated bursts. Also, we searched for the PRS with ATCA, But because of the sparse UV coverage, we are keeping upper limit on the flux density of the order of 1 millijansky. So now coming to the second source, which is the well-studied repeater, thanks to the morning session for the detailed history of this source. So MeetRap collaboration has been already monitoring this source from 2019 and continuing through 2025. The observations are conducted by deploying the simultaneous beamforming and imaging backends of Meerkat, which allows us to look for any potential correlation between the properties of the PRS itself and also the burst. So the data from this initial monitoring was analyzed and published by, and so for the details, you can look at Manisha's and Lawrence's paper. So here I will discuss some of the other results from this monitoring campaign. So here I just show the DM estimates of this source from Meerkat compared with those values reported in literature. We find that the DM of this source is declining at a rate of 0.01 parsec per cubic centimeter each day. And this rate is also consistent with the results from FAST, indicating that there is a potential evolution in the ionic environment around the progenitor of the R1, possibly due to expansion or the clearing out of the local material. So what's happening to the PRS? So here we have been also monitoring the PRS with Meerkat over the years. So here I just show the light curve of the PRS. So we have Meerkat observations in 2019, 2022, and 2024, and also continuing through 2025. So the insert shows this Meerkat observation, high cadence Meerkat observation happened in 2024. So we find that this flux density of this PRS is exhibiting variability in the order within weeks to month timescales. And such a flux density variation is also well described by refractive scintillation, which can predict a modulation amplitude of 25%. And we find no evidence for long-term variation in the flux density with this source. And some detailed analysis on this scintillation is also yet to be undertaken. Also, as a summary, the MeetRap discovered a hyperactive repeater. So we have been long-term monitoring this source, and our observation revealed an exceptionally high burst rate. So most of the bursts are linearly polarized and exhibiting modest variation in the PA angle. So long-term monitoring is crucial to understand whether the source will become active again or will remain as an isolated outburst event. And no PRS has been detected across a frequency range from 0.5 to 12 gigahertz. And we found an evidence of RM evolution with no significant evolution in the DM. And also long-term monitoring of R1 indicates that the DM is declining at a rate of 0.01 parsec per cubic centimeter. And the flux density variations is agreeing with the predictions from refractive scintillation. Thank you.
Thanks, Kavya. Do we have any questions? You? Okay.
Hi. Yeah, thanks for the great talk. I'm wondering about FRB 121102. If you combine the change in dispersion measure with the change in rotation measure, what sort of magnetic field do you get? I'm wondering because it seems like it would be a cleaner measurement than just the RM alone, which requires knowing the host DM, which we don't.
Yeah, I think I haven't done such an estimate because we don't have RM measurements alone from Meerkat, but we have RM estimates from other telescopes, but we have values till 2023. But all these measurements of Meerkat is also from 2019 and 2022 and 2023. So we don't have simultaneous RM measurements, but it's it's a good analysis to check whether there is any the estimate of the magnetic fields with the estimate. Yeah.
We have another question for Jane.
This is Brian Gainsler from UC Santa Cruz. Thank you for that talk. What can you say from the latest data about the possible periodicity in R1's activity period that had been suggested previously?
So could you repeat the question again?
So there had been a claim of a possible periodicity, 160
Yeah.
days. So does your newer data through to 2025 support that or lower the significance, or not sure?
So I can just show here. So we have detected burst only in 2019, 2022, and 2023. These are well within the activity phase described by the 160 days periodicity. We don't have further burst detection in 2024 or 2025. But recently, I also saw in an ATEL that in 2 months back, the source has become active again, and this is consistent with the predicted periodicity cycle. But we don't have any detections from Meerkat.
But you were observing during the predicted activity periods and didn't see anything in
Yeah,
24
actually, we had a single observation in the last May in the predicted periodicity, like within the active phase, but we did not detect any burst in 2025.
Thank you.
Okay, we have time for a short question. So one over there.
Where am I throwing it?
Nice. Hi, Marilyn here. I was wondering regarding the follow-up of 12.11.02. So do you observe it like randomly when you have some time to observe it, or when you think it's detected, or there is some indication that was active?
So the observations happened in 2019 and 2022 were 2022 and 2023 were DDT observations. So we had only few observations within the activity cycle. But the observations happened on 2024 was we had the Meerkat proposal and we got time. So we arranged the observations in such a way that it was in a logarithmic fashion within the activity phase, also in the inactive phase. So that's why we had 3 observations within a week. Then the separation between the observations increases in a logarithmic scale. Yeah.
Thank you.
Okay, if you have any more questions, please ask them during the coffee break or on Slack. Let's thank our speaker again.
Should I just skip this?
And now we have 2 flash talks. Just a note that we have switched the order of the speakers that were scheduled.
Those Google Slides, yeah.
Can you hear me?
All yours.
Can you hear me in the back? Great.
Okay, so our next speaker is Thomas Abbott. So please go ahead.
Thank you. Yeah, so I'm Thomas. I'm a master's student here at McGill, and I work with Professor Vicky Caspi and Dr. Aaron Perlman. And today I'm going to be presenting some results from a long-term monitoring campaign using the CHIME pulsar instrument on FRB 2022-09-12A. So because it hasn't been introduced yet, I'll just talk briefly about the CHIME pulsar instrument, which uses the same front end as CHIME FRB, but it differs in the back end. So CHIME FRB, as we've seen, forms these static beams in a strip along the sky and scans the northern sky every day. CHIME pulsar, on the other hand, has digitally formed tracking beams, so we can point at a source and follow it through its transit. So it's a little bit better optimized for targeted follow-up. And in particular, we use it a lot for follow-up of repeating FRBs. So in this talk, I'll be describing or discussing 2022-09-12A. A lot of you have already written papers on this source or are familiar with this source, but it was discovered in 2022 by CHIME FRB and quickly localized by the DSA. And then later that was improved to milli-arcsecond localization by the EVN. And most notably, it had an enormous detection rate, over 400 bursts, or about 400 bursts an hour from FAST. And there have been a lot of other scientifically interesting results from this source, including microshots, a drifting central frequency over time, and as I'll discuss today, some DM variation. So basically in this project, we study the source for about 2 years. We have 20-minute observations every day, amounting to over 200 hours of observation with CHIME pulsar. And we detect about 800 bursts from the source. And just by calculating the total energy emitted This is a very rough estimate, sort of back of the envelope calculation, but I think it's an interesting result nonetheless. If we calculate the total energy emitted by the source and approximate scaling up for times we're not observing and also for the radio to X-ray fluence ratio, we get an energy emitted over this 2-year time span of something like 10 to the 40 ergs, which is already getting sort of within an order of magnitude or so of the amount of energy stored in a magnetar's magnetic field. So I think this is further motivation for following up these hyperactive repeaters as they can test some magnetar models. Okay, and the other result is over the 2-year time span, we saw a pretty steady linear increase in the DM of about 1.3 parsecs per centimeter cubed per year. This is using the brightest, narrowest bursts. You can see that increase. And interestingly, there's no corresponding change in the RM. It remains consistent with 0 throughout the observations. So yeah, I'll just stop there. I think I'm out of time. Thank you.
So much. Have any questions from the public? No? Maybe like, are you also following up other repeaters that show similar properties, or is this the only one so far?
Yeah, we're following up a few repeaters. Mostly our campaigns are dedicated to nearby repeaters, and we want to trigger high energy follow-up. But with a lot of those sources, we just don't detect any bursts.
Okay.
So it's a bit of a mix with nearby and kind of high-risk campaigns and also hyperactive.
Okay, yeah, thank you so much. Any other questions or online? Okay, if not, let's thank our speaker again. And lastly, we have a pre-recorded talk by Param Joshi.
Okay.
And I believe Param is online to answer questions as well. It was...
Yeah, that was a PDF. All right. Oh, sorry, I'm just anticipating an audio problem. Once I start it, if people on Zoom can that we hear it. Oh, sorry, I need to restart this. I lost my Chrome window. Sorry. Because I think I need to reshare the screen with a audio shared. Could be. Oh, great. So we were golden.
Hello everyone, I'm Param Joshi, final year master's student studying at the National Institute of Technology, Rourkela, India, and I'm also currently an astronomy student. Today I'm going to talk about this particular FRB and our observations with the LN telescope array. So let's first begin with a bit of an introduction on the telescope. It is an array of 42 antenna dishes, which is spread across the Hat Creek Radio Observatory in California. And each antenna is 6.1 meter in diameter, and it covers a bandwidth of 1 gigahertz up to 11 gigahertz, with 2.68 gigahertz of instantaneous bandwidth. And currently 28 out of the total 42 antennas are being used at 672 megahertz wide and independent bands simultaneously. So let's start with some of the observation statistics. We observed this source for a total of more than 1,000 hours, and at frequency ranges of 900 megahertz all the way up to 7.6 gigahertz. And we have detected a total of 97 bursts using the SpunDuck plus ML pipeline. And the bursts covered the frequency extent from 900 megahertz to 5 gigahertz. And the fluence ranges was 15 to 300 Jansky milliseconds. And the bursts show some usual subburst structures and downward drifting patterns. So on the right, we have the plots for the on-sky time of the source as per the frequency that we observed. And the below plot is just a random subburst showing structure of the FRB. So these are our results with the LN telescope array. And we detected around 20 bursts, which are wideband in nature, with a bandwidth of 800 megahertz or more, and burst energy of more than 10 to the power 40 ergs for these particular wideband bursts. and the burst rate was observed higher in S-band than L-band, but we are still investigating the impact of RFI in L-band and also some issues with the pipeline that it could not detect the very low SNR bursts maybe. And yeah, it is also possible that due to either higher burst clustering at S-band than L-band, or maybe it was an active period of FRB at the time we were observing the S-band. So on the right, we have the plots for the burst rate and as per the frequency. And the below plot is for the burst clustering. We can see that the clustering is higher in like S-band around 2500 or 3000 megahertz. And also we have a higher burst rate at around 3000 megahertz. So that may be possible because of that. So these are some of the detection plots. It is a beautiful FRB showing various substructures of the burst, and it's also having very wide band emissions and highly energetic bursts. So yeah, this is going to be my future work to study all the spectrotemporal analysis of the burst with some properties like width, drift rate, bandwidth, and analyzing all its variations with frequency, and also some burst energetics and rate and clustering. And yeah, please feel free to reach out to me for any questions or comments. And I'm open for any questions if we have time, and I'll be online as well. Thank you.
Or Param? If not, since we're a bit short on time, we'll go to the coffee break now. We have until 3:30, so 20 minutes. So see you again then.
Can people see my screen?
Yeah. Hi, Sunil. We're just giving it 1 or 2 more minutes for people to get back to the room.
Sounds good. Can you see my screen though? Oh, thank you.
Brinson fellow, and then afterwards we'll transition to a discussion section where we'll have Karen and answer time, and Nicholas Taylor's leading us, and then afterwards, kind of as a part of that, we'll be splitting into various subgroups. Some here, some in some of the groups upstairs, some maybe out and about in the lobby, and then breakout rooms. So without further ado, take it away, Sunil.
Okay, thank you very much. Hello, hey everyone. My name is Sunil Simha. I am a Brinson Fellow at the Northwestern University and the University of Chicago. And today I'll be talking about getting redshifts when we will be having thousands and thousands of FRBs. Basically, how can we convince the time allocation committee that you're going to give us telescope time in that era of plenty. There we go. As Ashley Viller mentioned yesterday, we are in a very nice state of affairs at the moment. Transient discovery rates are increasing across the board. And this is especially true of FRBs, whose numbers are only growing exponentially. New generation instruments are right around the horizon, and we are expecting them to produce a few thousands to 10,000 or so FRBs every single year, which roughly translates to order 10 or order few to 10 bursts per day. And most of these instruments will be producing very precise localizations. CHIME is already on its way to produce 200 subarc-second localizations per year. And I will take this opportunity to show off, as everyone else has done before me, FRB 2025-0316A, which CHIME was able to localize to 50 milliarc-second precision, and we were able to do some pretty cool analyses that Mawson will be talking about later in the conference. Basically, if you look at the JWST image at that location, you could see there are individual stars, and that's pretty neat. But that said, we will therefore require, because we're going to get precise localizations, the host associations will be more or less robust for every single one of them, and therefore getting Z host or host redshifts is essential. We need lots of them even. Now, of course, this is not to say that you cannot do science without having FRB redshifts. Here are a few examples of some wonderful science that you could do just fine without knowing where your FRBs are coming from or even how far away they are. So Matt McQuinn talked about work done by his student and him back in 2023, where they measured or tried to measure the radial profile of baryons in foreground galaxy halos. Lord Kahinga will be talking about a similar effort, utilizing roughly the same-ish machinery, but focusing on the M31 halo alone. Stay tuned for his results later in the conference. And also Hao-Chen Wang, who's leading this DM cross-correlation with foreground galaxy photo Z catalogs to gain some interesting insights on the baryon distributions in the universe. So you could do a lot without host redshifts. But at the same time, if you had host redshifts, you could do a lot better. And in fact, many of the previously mentioned analyses would improve, especially in the era when you have thousands of FRBs. In any of those samples, having redshifts is really, really useful. Here are all some examples. Starting with, of course, the McCart relation-esque and related analyses that you could do with a sample of FRBs, as shown by Liam Connor in his most recent paper, and Kriti Sharma as well. Of course, you could do flim-flam-like analyses. Here's one of the sight lines from the flim-flam DR1, published or led by Ilya Kraikin. You could be doing host properties, analyses of normalized offsets. Guess what? You need to know how far away the host is to measure any of these. So you need redshifts. At the same time, if you wanted to measure host galaxy properties such as stellar mass or star formation rate or anything that requires SED fitting of some kind, it's great to have redshifts. Radio analyses too, like the one that Masen Salmons showed in his 2023 paper with the two-screen scattering analysis, that definitely makes use of the distance to the source. So you need redshifts for that as well. In short, if you have an FRB, it is much cooler with a redshift. So it's good to have these. Here is the team that is likely supplying you with all your redshifts. We are in a great privileged position to be able to collaborate with numerous radio detection, FRB detection experiments, and do a lot of cool science thanks to our optical expertise. And as you can see, our numbers have grown somewhat over the recent years. And it's always exciting to be working in optical follow-up. So I want to lead you all into what goes into measuring redshifts. What do we do exactly? How do we go about doing it? The first step, of course, is to identify the host galaxy and in more quantitative terms, robustly associate it with the path framework. And for this, you require sufficiently deep imaging. Most of the time, we just rely on public imaging databases. So these usually go up to a magnitude depth of 23.5 in R band. And if you have much fainter hosts than that, so this is not very deep for people who don't think about magnitudes on a daily basis. At least not deep for 2025, maybe back in the day. But if you want fainter hosts, and which happens quite often, you need to go with deeper observations. And sometimes you have to waste a lot of telescope time as well. Take, for instance, this NearCam image that Adam Deller showed last year in the FRB conference of 210912A. So this is a 78-minute image in F150W. And at the FRB location, you could see there's a very, very faint source, which I think is a 29th magnitude source. But before you could get here, you had to do deep follow-up campaigns with 10-meter class telescopes and convince the JWST TAC that indeed you need space-based imaging to get there in the first place. Here is another such result that Dante Hewitt and others presented in 2024, where if you got much deeper image, you realize that the association of your FRB to this faint galaxy improves, as opposed to having something like one of these bigger blobs, which could be the host. So if you wanted to identify dwarf galaxies or very low luminosity galaxies, you'd better be doing deep imaging. Otherwise, it's really hard to even see them. There are quite a few imaging surveys just around the corner. So one example is Euclid, which basically covers both the northern and the southern hemisphere, or good parts of it, in these blue regions that I'm showing here. So this achieves something like magnitude 26 or 5 sigma depth in the visual band in 6 years. Similarly, LSST has come online, and it will be reaching magnitude 27 limit in R band in 10 years. Although you will get pretty deep soon enough with it. It's just a waiting game. So to identify a host galaxy, which telescopes would you use? Firstly, of course, you would start with legacy imaging and see if there's anything there. Now, this can be a little tricky, and as you can see in these survey coverage maps showing for hand-stars and the legacy survey as examples, the depth of the imaging can be dependent on where in the sky you're looking at. So for certain patches of the sky, you have pretty deep imaging, and sometimes it goes, so pan-stars goes down to something like 23.5 magnitude, but there are quite a few areas where the depth is not that great. Similarly, with the legacy survey in the south, there are regions which, for instance, covered in the DES survey, where you could get pretty deep, but this is not true for every patch of the sky. So you might require specialized or like dedicated imaging of your own, and you could achieve this with various telescopes. So if you have a 4-meter class telescope and you push it to an hour of integration on any given band, or let's say R band, for example, you could reach a depth of roughly 25. And if you push it for maybe 2 more hours, then it becomes like 25.5, perhaps. So it's a numbers game where the exposure time, so basically the signal to noise goes as the square root of exposure time. So you have to integrate for much, much longer to make significant gains beyond this. With the 10-meter class telescope, the story is similar, but you could go deeper with 1 hour, so 27th magnitude. And of course, if you have something like JWST, then you could go down to something like the 30th magnitude, which is really, really faint. But that, again, requires 1 hour, and that is not easy to get. And many of the times, to go to JWST, you have to first do 4-meter and 10-meter, or like 10-meter class imaging, basically show that you cannot do anything from the ground, and only then will you be awarded time to do JWST observations. So it can be challenging, even to just identify the source. Now, let's say you have identified the source, what next? So you could first turn to public spectroscopic databases. Here's a few I'm going to flash very quickly. So if your host happens to be pretty big angularly, it's very likely a low redshift galaxy. And so there's a good chance that you might get its redshift for free within something like the 2-mass redshift survey or the 60F galaxy survey in the south. Both of them are not very deep, so median redshifts are something like 0.05. But hey, that it covers a very large part of the sky, so fingers crossed you get your redshift. Now there's of course SDSS, but that covers a much smaller volume of this or area of the sky. Here you have various surveys, all of them basically combined into what is called the extended VOS survey. But the part that is probably most interesting to FRB host experts or like people wanting FRB host redshift is basically the legacy survey, which is a magnitude limited survey, and that goes down to like 17.77 magnitude in this part of the sky. And you basically can get redshifts up to say 0.1 or so. If you're lucky, you could get all the way up to like 0.2. For very specific faraway objects, so if you have an ELG host or LRG or quasar associated FRB somehow, you could go for much higher redshifts, but the coverage there is much poorer. It's not the best, and more often than not, you will not get anything. DESI, of course, does much better than SDSS, and it goes deeper, and it also covers a slightly larger part of the sky. And by the end of its survey, like the full survey, you will have roughly redshifts for 1/3 of the sky, which is great. But still, there's a lot of the sky that's missing redshifts, so you have to get bespoke redshifts of your own. So just to summarize, there are public redshift catalogs, but they have limited coverage, so you have to get lucky to get redshifts within them. There are future surveys that are coming. Like I mentioned, DESI is going to be releasing many more data releases. DR2 is already ready, and like you could see the improvement from DR1, where a much larger part of the sky is covered, and also the parts of the sky that was already observed have deeper coverage or more complete coverage. Euclid and Roman are infrared experiments, and they will be providing slitless spectroscopy, which is not perfect, but it works if you have redshift greater than 1 hosts, which is very likely with the next generation instruments. In the southern hemisphere, the coverage is not that great. There's Foremost, which will be doing the wave survey, and it will cover a much smaller part of the sky than DESI. So for any southern spectroscopic follow-up, you will probably be requesting telescope time of your own. And now, if you were to ask the same question as before, for which telescopes to use for spectroscopy, you could pretty much use the same thing, but you would have to reduce the magnitude limit by 2 or 3 magnitudes for spectroscopy. This is simply because, as opposed to imaging. So when you're imaging, all the light is falling on a few pixels on the CCD. When you're doing spectroscopy, you're spreading this light across many, many more pixels. And so you have to have much brighter objects to get comparable signal to noise per individual spectral element. And so the magnitude limit gets fainter. So rule of thumb, you could say 2 or 3 orders of magnitude lower. So as you can appreciate, it is very challenging to obtain spectroscopic redshifts for technical reasons, basically because faint objects are hard to observe. Here is a simulation or calculation done by Lord Kahinga, where he tried to look at the CHIME FRB catalog, the catalog 2, got their dispersion measures, used the McCart relation, and converted them to basically distances, and tried to compute what their magnitude distributions might look like. And this is basically what do you get from that if you trust existing distributions for host magnitudes? So most FRBs for time will be peaking around like 22 magnitude. So you will most likely need a dedicated follow-up for these sources, and this will be doubly true for any next generation instrument, which will go up to much higher dispersion measures, and it'll be much more sensitive even. And then you could ask the question, how many of these catalog 2 FRBs are actually in DESI, and how many of them will have spectroscopic redshifts? The way you do that is by taking into account the various completeness measurements. So basically, if you were to target spectroscopically a bunch of galaxies, usually, so let's take for instance the DESI survey. The Bright Galaxy Survey sample of DESI will be targeting galaxies up to magnitude of 21. But because of technical constraints, not every galaxy will be followed up, or if it is followed up, it will not have redshifts for some or the other reason. So for the BGS sample, the Bright Galaxy Survey sample, you would basically have redshifts for 80% of the hosts. And this completeness fraction can go lower for the others, even higher redshift samples. So ELG and LRG samples, for instance, the emission line galaxies and luminous red galaxies, which are further away, will have something like 50% or even lesser completeness. So if you were to incorporate all of that information and ask what fraction of chime hosts do you expect to get free redshifts for, it turns out that it is, well, less than 25%. So that's not great. So we need our own redshifts. Then comes the social aspect of the problem, I guess, which is, well, currently we have a sample of 100 or so FRB hosts, and all of them with redshifts, that is. And they have various properties. They, they exhibit radio properties of various kinds and optical properties of the host galaxy as well. So a very diverse sample. Usually, whenever you go to a time allocation committee and say, hey, please give us redshifts, they ask the question, why do you need more redshifts? And we're at this awkward phase of time where we have a large sample that we could do interesting science with, but we would love to keep getting redshifts, and just incrementally receiving redshifts for, say, 10 or 20 or 30 more FRBs at a time is no longer attractive. So what we need to do is we want to be efficient about how we get our redshifts, and we want our redshift surveys basically to be more science oriented. Basically to say, okay, I want to do a particular science, and therefore I want to select a specific subsample of FRB hosts or FRBs themselves, and then I want to obtain redshifts for those. So if you have such a motivation, it becomes much more, well, it becomes easier to convince the TAC that you know what you're doing, and also you will be able to get redshifts for those. So here's a few thoughts I had in this regard, how to get redshifts. So one way to do it would be to heavily invest in multi-object spectroscopy, because in the future, when we have tens of thousands of FRBs with hosts, or we would like to get redshifts efficiently. So getting redshifts for a bunch of FRBs at the same time is much more efficient, as opposed to spending 1 hour per source getting just one redshift. And in this regard, I'd like to mention the Subaru Prime Focus Spectrograph, which is a fiber-fed instrument with more than 2,000 fibers, over a 1.25 degrees square degree footprint. It's got enormous, or like it's low resolution, but like medium to low resolution, I would say, wavelength with wavelength coverage going from 380 nanometers all the way to 1.25 microns. It's already operational, and we have been getting some really good redshifts. So behold, this is a single flim-flam sightline for which within 4 hours we have gotten 6,000 redshifts, as opposed to spending 40 hours with the AAT and Keck. So this is great. The other thing that's great about the PFS is that Q mode observing is the default, although for the flim-flam analysis, we went classical because of our specific survey strategy. So what happens is that if you provide them your targets, they will mix and match, or like they'll pull it along with other targets that people have submitted, and you will be observing in Q. So you will be further increasing efficiency of getting redshifts this way. So the other ideas I had was like to come up with targeted follow-up or subsamples for targeted follow-up. So basically, if you were to select 10 to 100 sources at a time for spectroscopic follow-up, then it becomes much more manageable to do. And so here are a few science ideas that I had in mind. So for instance, you could try to get redshifts of unseen dwarf populations. So this would have to be an extensive imaging and a spectroscopic sample a campaign where you could select for, say, the dispersion measure being less than 500 parsecs per centimeter cubed, and that way you would be selecting close by objects. Just a thought. So I'd love to hear your inputs on this. The other thing you could do is look for FRBs just behind clusters, or like one cluster, say, so that you could use something like the PFS and get redshift for all of those FRBs. And that way you will be able to try to make statements about the density field of the foreground cluster. And if you have SZ effect measurements along with the density, so where you could get pressure, you can get temperature profiles of the cluster itself. So that could be interesting. And then finally, if you wanted to do an unbiased sample, maybe, so for in the case of CHIME, you have a large density of targets in the northern hemisphere, or like, sorry, or just around the North Pole. So if you were to just place the prime focus spectrograph over there and just wait for, say, a couple months, collect a few hundred sources at a time, and then go hammer at it with a fiber-fed instrument like the PFS, then you could be pretty efficient at getting spectroscopic redshift for all the galaxies that you want in that sample. So you could do whatever McCart-esque analysis that you would like to do with it. Take, for instance, over here, I'd like to show so if you were to take all the published FRBs and look at their median or binned mean DM extragalactic as a function of redshift, you could see the sort of trend that is increasing, that is expected. But if you were to ask the question whether the host dispersion measure contribution to these galaxies also has a redshift trend, then you could kind of say maybe. Of course, it gets sparser as you go out over here at higher redshifts, but at low redshifts, you could see that the binned median is very much consistent with McCart plus 80 parsecs per centimeter cube at the host redshift range. So this value is from Lucas Bernales' latest paper. Please go check it out. Or as you go to higher redshifts, and now this could be very much a small sample effect, you could have closer to Clancy James's 186 parsecs per centimeter cube from a much earlier paper. So if you wanted to study the redshift evolution, then you would love to have some sort of unbiased sample like this, for instance. So a couple of other things to consider in the last minute that I have is maybe we could consider crowdsourcing FRB redshifts, report your FRBs for optical follow-up. DSA 2000 is already planning on making all of their FRBs public. You could just produce a sample of boring or typical FRBs, just report their RA DEC DM, nothing more. And this in and of itself is good enough for many optical follow-up science cases. Maybe collaborate with teams that have massive multiplexing capabilities. If you don't have a Japanese collaborator yet, I think this is the time you go talk to someone and get some Subaru time. DESI 2 upgrade will have 10K fibers for targeting really high or redshift greater than 1 to 2, or like between 1 and 2 sources. Maybe some sort of TOO spare fiber program could be of use. Maybe also consider creating infrastructure to share these FRB hosts and also host optical follow-up data. FRBhost.org is a resource that we have currently, but maybe it could be, I don't know, maybe you could add more bells and whistles to it. I don't know. Things for you to consider during the discussion session. So I'll leave you all with this summary. I'm happy to take any questions. Sorry, I went a little over time, I think. But thank you all for listening.
Great. Do we have any questions in person or online? Saw Matt Dobbs' hand shoot up.
Hi, it's Matt Dobbs here from McGill. For our future next generation instruments, we're already thinking about how to target the most interesting FRBs by changing our selection function, let's say for high dispersion measure or certain locations on the sky. You covered that a little bit, but it also means that our follow-up could be more interesting and time-consuming as the sample is selected to be further away and these instruments go deeper. One thing that we have not considered is whether to bias our samples towards those regions of the sky where there's already a lot of optical information, like the DESI regions of the sky. Should we be considering that? Should we be saying that, you know, in that region where there's already a lot of redshifts, we should have a different lower signal to noise ratio cutoff?
Oh, I think that's a great question. Now, of course, like whenever you're making your selection function more sensitive to a certain part of the sky, then you're obviously introducing biases of various forms. And especially if you're optimizing for something like DESI coverage, then you might be limited to very low redshift follow-up observations. So if you were to say, I only want FRBs with DM less than 500 so that I could hope that a reasonable fraction of those will have or DESI redshift already, then, I mean, you could still do decent science with it, but I think it becomes a careful matter, or like a matter of careful consideration as to what biases are introducing. It could be worth it, is my answers.
There's a question online from Shami. He has a question about multi-object spectrographs. They don't really help with multiple FRBs, right? They just get us a bunch of redshifts in a given field.
So I guess I should have been clearer. So the idea is that because FRB host redshifts are not really time sensitive, the galaxies are just going to be there. The idea is to build up a sample of FRBs in a region of sky so that it's dense enough for multi-object spectrographs to go and follow up with multiple FRBs at the same time, FRB hosts at the same time. I hope that clarifies things.
Right, but that you're talking about now in era of 100,000 FRBs before you'll have multiple in a square degree.
That is fair. Yes, that is the.
I mean, we'll get there, but not yet.
Definitely, not yet. In the more recent future, I think we should maybe focus on just figuring out what subsamples of FRBs would be interesting to do dedicated follow-up.
Hey, Sunil. Calvin here from UC Berkeley. I am a blissful optimist, and I want to express an extreme opinion that we just shouldn't worry about this problem at all. Because in the next era of FRBs, let me ballpark this, you're going to have 10,000 FRBs a year from CHORD, 10,000 FRBs a year from the DSA 2000. You're going to find 1% of those are interesting enough to deserve follow-up. And for the rest, you're going to get photometric redshifts from missions like Euclid, which will give you photometric redshifts for the 1 billion galaxies that they're going to use to do weak lensing. Weak lensing science requires accurate calibration of photoz's, and there are many, many people working on this. We should just completely outsource this problem. and ignore it for the purposes of large samples of FRBs, except for that 1% that you select that are the most interesting. I know this is an extreme opinion. Please talk to me at the break or something. I'll now hand the mic back to Alex.
I mean, I love your optimism, and I think there is definitely it's a valid statement to make. Yes, maybe you don't want to do dedicated follow-up or spectroscopic follow-up for a large sample, and honestly, given how things are, like how costly it is to get redshifts, yeah, I think that's the way to go. But yeah, I think people should be thinking about how to figure out that 1% sample that is interesting, is my point.
We'll do one last quick question by Casey, and then we do have a discussion section right after this. So everyone can fight Calvin then.
I'll support Calvin with a quick comment. You didn't mention SphereX, which is hundreds of millions of high quality photoz's, and that's all sky. So it's even better than Euclid in that sense because it's not biased to certain regions of the sky. So so this potentially could be a solved problem in some redshift domain, you know.
So yeah, I should have mentioned SphereX. Well, maybe you should clarify it for me, but from what I understand, SphereX does not have very good angular resolution, so you might be only limited to a shallow redshift catalog with their photoz's, but correct me if I'm wrong. Or at least you won't get unblended photoz's, is my understanding.
Thanks, Sunil. And we'll now move to our discussion section.
Thank you.
This one? You want it on the Google or as a PowerPoint?
Oh,
Because I don't think it's downloaded.
oh, whatever works. Google. Yeah, whatever you think.
Okay. But it was a PowerPoint.
It was a Google Slides.
Ah, okay.
Yeah. I guess I just when I download.
No, that's fine.
Oh, perfect. Thank you. Okay, can everybody hear me in the back? All right. Okay, so hi everyone. My name is Tara Nayeftakari, and I'm hopefully joined by my co-chair, Nicolas Tejos, online. And we were charged with leading the discussions. Yes.
I
Okay,
think
great.
the slides are not being shared online.
Oh, I'm not going to
At
touch
least I don't see them.
Right, thanks for letting us know. Just one quick second.
And hi, everyone.
Hello. That's not your slide. These are slides.
Perfect. Thank you. Okay, so we are going to lead this discussion session, or at least prompt you guys with a few questions that'll hopefully help to motivate your discussion sessions, the breakouts. I think luckily for us, Sunil did a really nice job kind of summarizing some of the main challenges that we'll be faced with. Already heard some spicy remarks from the audience, so I think this will hopefully lead to some really good discussion. But yeah, so the key questions that we are thinking about for this discussion is, as we move into this era of thousands of host galaxies, how do we avoid biases? What are the selection effects when it comes to analyzing FRBs as a population? And finally, how do we actually obtain the required number of host galaxies? A great point that Sunil made is, you know, one way to maybe think about this, there's no way that we're going to get redshifts for absolutely everything. So we should really think about this from a science question perspective. What are the key science questions that we want to answer?
And those questions are going to have different types of galaxies, for example, or properties that we need to measure to answer those questions, right? So really just keeping in mind the science question you want to answer and what kind of sample you need to do that. And those different questions will require different strategies, and each of those strategies are going to have their own inherent biases. So something to keep in mind. Also, keep in mind that there are basically always going to be unavoidable biases. So I think there's really no way around that. But our goal is to just better understand them and think about how can we construct experiments to kind of control for these different biases and maybe compare to one another. And then finally, second point number one is that we should keep in mind that there will be biases not only in the host galaxy follow-up, but also in the FRB detection, right? And we heard about this in the context of CHIME from Kyle earlier today, but there are these different selection effects that are inherent to FRB experiments. And so it's very complicated if we're comparing populations of hosts from one experiment to another. It's important to keep in mind that they could be inherently probing different populations based on these selection effects. Imaging strategies, as Sunil mentioned, most FRB experiments right now are relying on the fact that we're using basically public imaging to identify host galaxies. And so what this means is we're really not sensitive to low luminosity dwarfy things or even high redshift galaxies. So hopefully this will be, better facilitated with Euclid and Rubin. But again, something to keep in mind that kind of right now we are biased against detecting those things. And so this will necessitate deep optical IR imaging to really try and go after these faint sources. And as Sunil said, that's not trivial. It takes a lot of time. And so one of the things we should be thinking about as a community is how can we kind of optimize use of those resources. And then similarly for spectroscopy, I think these plots here are really pretty telling. You can see that there's this huge dearth of spectroscopic redshifts above about Z of 0.5. And again, that's because as you go to higher redshifts, it just becomes significantly more challenging to get a spectrum. So again, we need to think about what science questions are we trying to answer at higher redshift, and how do we really try to fill out that high Z parameter space with redshifts. If your goal is to just get a spectroscopic redshift, there's probably some duplication of effort happening in the community. So is that something that could be better coordinated? And then of course, maybe these multiplex fiber-fed spectrographs could really help in this domain. And I'll pass it over to Nicolas.
Yeah, thank you, Tarane, and hi everyone. So yeah, following up on these open questions for the discussion, the second question is the selection effects. How do these are important for understanding or studying FRBs as population? And one of the things that we have learned from this quote unbiased surveys in which a magnitude limit and a set of criteria are defined before the follow-up is that we are really biased towards nearby bright galaxies. So yeah, obvious questions that remain to be answered is, are we selecting against low mass dwarf galaxies and any other bias? And so far, we have been just talking about getting a redshift. And that's already challenging for redshift higher than 0.5. So characterizing the galaxies, so a different question, a different level question on how are the stellar masses of the galaxies, star formation rate, demographics in general, or even resolving the galaxies and where the FRB pulse is coming from within the galaxies poses a much higher challenge on this topic. So perhaps, yeah, for some questions, this previous statement about we don't need to worry about this is fine, but there are some questions that we really need to worry about it, even with wide spectroscopic redshifts or photometric redshifts available. Yeah, So yeah, I'm going to skip a few of those questions. Can you go to the next slide, please?
Yes.
So then the final question that was we wanted to have an opinion from the community is how do we obtain the required numbers of host galaxies? And of course, the required number depends on the science. But coming back to this idea of coordinating efforts, and it's a topic that has been brought up in a few times in this week and in previous conferences as well, is about whether it's convenient or not to make FRB information, localizations, or key properties immediately public for the community, and yeah, consider the pros and cons of that, and what kind of science could this facilitate if you work more coordinated within the community. Back to how to prioritize targets. Yeah, in the era of plenty of FRB localized, I think the experiment is inverted, so we don't need to follow everything. We need to pick this 1%, 10%, or subsample of available FRBs for answering the specific science question we want. And it has been mentioned already a few talks for cosmology, and also the previous comment, which I forgot who gave the comment. That's why I'm not saying the name, because I didn't get it. But about just working with photosys. What can you do with photosys without worrying about spec-sys? And I think, yeah, that's next slide, please. So we came up with some brief answers to this. These are not, of course, unique answers. It's just one set of answers. So how do we avoid biases? As a summary, I think that the short answer is we don't. We just need to understand them. How do we avoid or compensate the selection effects? And again, these are unavoidable, and we just need to understand them, so to take them into account in our interpretations. So that's very important, because sometimes we forget, or yeah, it's easy to forget that you are considering one particular type of polls, or you're trying to answer a particular science question, and there are unknown biases in your own way of think about the interpretation that can lead to a wrong path in getting the best out of what we can do with the current technology and available resources. And then, yeah, back to the third question, we need to prioritize the follow-up, this 1% interesting or 10% interesting, based on the science question. And yeah, different science questions will require different strategies. And I am of those that think there are some questions that do require worry about getting redshifts of the hosts. And not just the hosts, but also perhaps the foreground structures, because the public surveys in the near future are not going to go very deep for redshift beyond 0.7 or 1. So I think we will still need to worry about dedicated follow-up strategies. Yeah, but now let's back to the discussion. So the idea, next slide, please. Yeah, we were asked to come back to this schedule. So I think people in the room over there will split in different rooms and work on these topics. And people online also will be split into different rooms to develop on these topics. So.
Okay, great. So hopefully everyone in the room can find themselves on this list. Room 217 and 328 are upstairs.
Yeah. So there's an LLC member assigned to each room. So that LLC member identifies itself and then looks at follow.
Okay, and then online, they're going to break you out into breakout groups. And then when are we reconvening? When are we reconvening? because we reconvened like the first time.
I just got invited to a breakout.
Nice. I figured I'd leave them up for people in the room. Yeah, I think that's a good idea. I'm just gonna make Nick the
The breakout rooms are gonna end this.
Yeah, Alice is that they were too small, so we'll just do one breakout room, but I just want to make sure that it's not too loud. And then we need to make Nick the co-host, and that's what I'm having a hard time.
Hello, we are back in the main room apparently. So not sure what's going on. Okay, only one online group here. That's fine. Is this okay? Okay, so is it okay we speak here? Yeah. We got on mute, so okay.
I can hear you. Yeah, I can hear you.
Yeah, no, but we are in the kind of physically, the computer is in the main room, and apparently they muted us over there, so we can talk here without disturbing them over there.
Sorry, can I have a quick question here?
Yeah, please.
Yeah, I saw in the meeting today, they were talking about, I think they want to relate the JWST for redshift measurement for FRBs. That's what I understood. That's correct?
Yeah, I think there was an answer. Well, there will be a talk. I don't know if it's tomorrow or during the rest of the week that Manisha Kale will present some high redshift measurement of a meal-trap FRB.
Yeah.
And today, I think it was presented James Webb observations of a more local FRB, but super localized.
I see. And then what is the range of, I think for the chime, the redshift is 0.5, yeah, for chime measurement. What is the highest redshift they have observed, any FRB, right, so far?
Yeah.
You have any number?
Yeah. I don't know from time, but Lodrick might know if he's here because.
Oh, I see.
The exact number. I don't
Yeah, the highest redshift from chime at the moment, it's not too high. I think probably around 0.3, maybe.
0.3, I see.
Yeah.
But what about other, I mean, for example, ASCAP or other radio telescope, what is the highest redshift, any source, any FRBs, the host galaxy, measure?
I think DSA currently holds that, or at least as far as the published literature is concerned, DSA holds that record at 1.27.
Oh,
or
1.27. I see, 1.27.
And there is also the ASCAP one at 1.1 something.
Oh, I see.
But we will hear from unpublished higher ones during the week as well.
Someone did a calculation, I think Clancy did some kind of calculation to see the Mia trap can actually provide the best redshifts, I believe.
Yeah, because of the sensitivity.
Yeah.
Yeah, I'm still coming back to this original question of how do we make the best of the resources we have. If we want to go to Redshift higher than 1, I think we will need dedicated follow-up, as I said. I don't know if you agree, Sunil and others in the room.
And for instance, if we go to higher redshift, then we can understand the ergodic time from far away and early time, maybe 10 billion years, maybe 9 billion years, maybe 8 billion years, right? That's the
and also all of these kind of nuisance terms when you want to do intergalactic medium or diffuse baryon distribution, which are coming from the Milky Way or the host itself, they get smaller when you go to higher redshifts. Also, there is this nice idea of proving helium reionization at redshift 3. That's still a spec. I mean, it's not feasible yet because we haven't got any high redshift FRB, but in principle, the energies, I think they imply that with sufficiently sensitive radio telescope, you can get them.
So, I guess maybe to circle back on the issue at hand is, I think it was an idea was floated, I don't remember when, at some point, about the entire community sort of collaborating. And so first and foremost, just sharing FRB data, and then the next step would be deciding what is interesting. And I guess high redshift, so technically high DM maybe could be one avenue where sort of people are sort of thinking about that. So I guess could that be a criteria, for example, for sort of figuring out what FRBs are interesting in terms of follow-up? And here, I mean, the whole community sort of, instead of like we have a bunch of FRBs that we all sort of share the resources and just go follow up. So maybe high DM could be a criteria. And so maybe you can have a high DM from ASCAP, a high DM from Mietrab, a high DM from Chime maybe. And the whole community sort of, we'll utilize our multi-regulatory facility to try and follow up that. Would that be kind of something to do maybe too?
Yeah.
And I have one more question for you. I'm not working on FRBs. It's not my field. Using SKA in future 2030, then it's gonna make us possible to detect more FRBs, right? In low FRB, I mean low SKA or mid SKA. I think now MidCat is working, but low SKA less than 1 gigahertz, I think is gonna help very much because, right?
Yeah, definitely. So ASCAP is kind of a prototype on that, right? Or I got the frequencies wrong, but yeah, totally. SKA is the next radio machine that we should be considering, definitely.
Yeah, so as I was saying, maybe if it's possible, can we have an established sort of threshold or baselines of what FRBs are important for follow-up? And I think, and how would we get buy-in from every other sort of part of the community?
I think those are so flexible because you have so many different questions that the answer to that subsample is going to be so dependent on the question. But here is an analogy, perhaps just thought about it. So when we have thousands or 10,000s of FRBs to follow up, then it's like the stars. So we have so many stars. We are not following all of them to understand the stellar evolution. We just make samples of stars to put everything together. No one is trying to get all of the stars in the Milky Way observed with spectroscopy, with all of the measurements that you can get. So I think we will be in that kind of position. And what Sunil pointed out is like, yeah, we can be we can be patient, and then at some point in a given area of the sky, perhaps we have enough FRBs coming from known or identified FRB hosts, which multiplex spectroscopy makes the most sense for being efficient. Yeah. And
I guess, yeah. Sorry, continue.
No,
yeah. No, I guess, yes, it makes sense for that kind of science, but I feel like that would take a long time to fill up a 1 degree square area in the sky. My thinking was more in the line of we all have, there's some combination of us that have some kind of time on some particular resources. And so I guess, but I guess that the biggest problem here is how to get buy-in from everyone. And so what I'm trying to come up is some kind of algorithm to figure out, as a community, what kind of questions are we trying to answer? And then from that, then figure out the threshold. So maybe like some kind of decadal kind of situation. These are the questions as the FRB community we're trying to answer. And these are the FRBs that will be interesting for said questions, and then go ahead and utilize all our resources as a community instead of, everybody competing for telescope time and proposals and things.
I think that's a great idea, but I guess circling back to your interest in high Z or high DM FRBs was to basically get redshifts for far away FRBs. So to which I guess the question I would like to ask you is why? As in, what is your science goal? And I think starting to define that would be a great way to start, and then like basically lead the discussion.
Why? Oh, okay. I think Nicholas raised, and first and foremost, the highest FRBs we can observe are Redshift 3, I believe. So all the science will have to be confined into Redshift 3 and below, I would guess. And so what kind of science can you do with Redshift 3 and below? Let me think.
I have this question for all of you, if you don't mind. In terms of, is that possible, the collision of two black holes when they are merged originate FRBs? Is that possible in terms of theoretical or observation? I don't know.
Yeah, I think we really don't know. So I think it could be. Yeah, it's a high energetic phenomena. I don't think it's being ruled out. But I'm not an expert on particular physical mechanisms for driving these pulses. But magnetic fields are everywhere. So if you wrap them and get them very dense, the energies, at least they don't. Yeah, order of magnitude energies can give you.
Yeah.
But the exact mechanism, I don't know if that exists. Sunil, you know more about that?
Not particularly, but from what I remember from, I guess, a discussion I had some time ago was that such a scenario would produce a lot of debris and basically a dense circumburst medium that could potentially scatter out any FRB that would have been produced during the time of the burst itself. or like the collision itself. So maybe if there is an FRB possible from that channel, it would be delayed after the formation of whatever collapsed remnant or the merger remnant. But others, please feel free to correct me.
Yeah, but you can also, well, you can, that's fair. It's basically, yes, so dense environment that you don't see because of the highly dispersed. You don't detect them. But similar to the supernova scenarios, when you also have this expanding shell of free electrons getting less dense and less dense with time, there should be a time when this is optically thin for the radio, right? Or sorry, not optically thin, but low DM for the radio pulse. Yeah, I really don't know. So yeah, I'm well, myself and I think others in this meeting here in this conversation now, we use FRBs as tools for proving the diffuse variance in between. That's probably our main driver. So that's kind of the same question we want to answer, and the strategy, of course, is quite different when compared to actually understanding the progenitor.
Nice.
So
thank you.
Yeah. No, for understanding the progenitor, I think the future is in the low redshift when you can resolve the galaxies. The high redshift will give you extreme energies, right? But you can also get extreme energies in the low redshift universe, I guess, but that you are limited by volume. So when you go to high redshift, you have more volume. Also, galaxies and stars do different stuff at high redshift than low redshift that will also give you clues for the progenitors. So, and just to wrap up on coming back to the strategies, some of the future surveys which have a lot of fibers sharing the focal plane, like Foremost or Weldesi or PFS, right? PFS. Yeah, at some point, because yeah, they might work better in Q4 in a Q system. So you don't need to find a high density in 1 square degree. You just need to find enough targets that are reachable within one night, and then I guess the scheduler will find out what is the most optimal way to point a telescope. So coming back to Lodrick's point, you really don't need to get to very high densities in the sky. You just probably need 1 per square degree or a couple of per square degree. I don't know. I haven't worked this number particularly, but you, Sunil, might have. What is the density that when this schedule will become more efficient than just going for the classical?
I haven't done that math myself, but I would imagine it would be when you have at least a sizable fraction of whatever 2000 odd fibers that you have in there. So maybe beyond 10%, that could start becoming more efficient. So that would require like 200 targets per square degree of sky. So that is solidly in the era of, I guess, hundreds of thousands of FRBs. Not anytime soon.
But you are thinking about one night, or I'm thinking about one semester.
One night, or I guess.
No. I'm not sure if your numbers work for one semester, because in one semester your proposals are per semester, right? Or not?
I think that's a good point. Yeah, maybe a fraction of that then. I think it also depends on like what other programs are doing during that semester. So
yep.
Maybe the strategy here would be to just give all the FRBs all over the sky that are that could be useful to get redshifts of, and just hope that
and then yes, and then sample from them with a redshift. That's in foremost, because in foremost we share the focal plane, but it's a 5-year project, so you are basically preparing your targets for a 5-year period, and it's very complicated algorithm to establish where the fibers are going to be placed. But it's trying to maximize all the different sciences, which 18 collaborations within Foremost.
And I guess it's already late to join Foremost, isn't that the case?
No, it's not late. It's not late to join. I think, well, it's late to prepare a survey dedicated for fast radio burst. I thought about it at some point, but the numbers at the time didn't make sense for Foremost.
Right.
But these numbers could make sense for Foremost in 5 years from now, when we need to put new proposals. That's something I've been thinking of.
I see. So once the 5-year survey finishes, what is the plan for Foremost? Is there future surveys?
Well, I don't know for sure. The funding and all of that is always complicated, but this is a huge effort. So I doubt that after 5 years they will say, okay, let's change the instrument and put something else. So I'm pretty sure the science we will get from Foremost is going to be motivating enough for continuing at least another 5 years and perhaps more. So I'm optimistic on that. But again, Foremost is a 4-meter. It's in a 4-meter telescope. So we're not going to be able to do this for high redshift universe. High meaning redshift higher than 0.7 even. So not even 1.
Right. I guess in that vein, so the question that was asked to me, I wonder if other people have thoughts here. What is the cost that we would pay in terms of biases if we did dedicated FRB or detections within spectroscopic footprints of known surveys, say DESI?
So can you repeat the question and see if I...
Sorry. So basically, if you were to just get FRBs within the DESI footprint, what would be the biases that you would be incurring from that sample of FRBs? So,
but that's assuming that you will not get a dedicated spectrum of your host.
Basically, if you rely entirely on DESI for your spec-Zs, and you only observed or detected FRBs within the DESI footprint. Or at least, let's say, maybe not. Maybe that's a bad idea. Let's say the majority of your FRBs are detected in the DESI footprint. Then
my point is that even when you think about the Sloan, it's worse even. But even with DESI, it's a very nice wide spectroscopy redshift surveys. But these are very complete, but not 100% complete. So the likelihood to get your host with a DESI fiber, I think, is very low. So you will.
That's true.
I think this is closer to 90%, but for a given magnitude limit, right? I'm not super involved in DESI. And also, depending on the redshift ranges, this is optimized for cosmological measurements. So they want to get bright things, easy to measure, and tracing the large scale structure in a well understood manner. So those are gonna whatever we get is just, if we just rely on DESI redshifts, we're gonna bias towards bright galaxies and non-star forming, even if you go to the high redshift or LRGs, so luminous red galaxies. So there won't be any star forming galaxy, and we know FRBs tend to be more in star forming galaxies. I wouldn't say that you can do a lot of science with just DESI redshifts. Of course, they can be useful, especially for mapping the foregrounds, perhaps. on megaparsec scales. But again, it's not enough for mapping the foregrounds, you know, Sunil, on hundreds of kiloparsec scales for halos, right?
I have this question for you. You are expert at the FRBs. This question comes to my mind because FRBs are the missing link for some celestial events in terms of cosmological events, because I think they should be answered for part of science, space science, when astronomy in cosmology and astrophysics. Do we have any that kind of understanding of where in the puzzle, where they fit? Yes, it makes sense to ask this question or no?
I didn't quite get the question specifically, but is it something about having a dedicated?
My question is this way, because as I said, I'm not an FRB expert. I'm not working on it. My question is based on astrophysics, on cosmology. They are missing link for part of science in bigger picture, in bigger map. We say, oh, we were looking for something else, but now FRBs, FRBs are the answer for that question.
It happened to me and very close collaborators. We were trying to find these missing baryons. There were 10 or some people from 20 or 30 years ago in the low redshift universe, and we were using what we had at the time, quasar absorption lines, either in UV or in the X-ray. It was very challenging because the quasar absorption line only give you access to the neutral atoms in a highly ionized medium, so you have to rely on huge ionization corrections, and even with quasar absorption lines, there is a phase in the intergalactic medium gas that is not particularly well suited for quasar absorption lines because it's not too hot and not too cold, so it doesn't produce a very easy to detect absorption line even the densities, which is called the warm hot intergalactic medium. But then suddenly the FRBs appear and they became, well, we know these are extragalactic, and they prove all ionized matter, so free electrons. And I think in a couple of years, with a very small sample, the community realized that all the so-called missing baryons are actually in the universe, so no crisis. We never thought it was a crisis. It was just a matter of finding where they are. It's a technological problem. And then, the answer to this long-standing question was provided by these new sources. And now we are moving to the next level of where exactly are these baryons to galaxies. But baryons are there. I'm not missing an important fraction of baryons anymore in the universe, thanks to FRBs.
Thank you.
And we probably should come back to the questions to give an answer, to give a summary answer from our discussions. Put the questions in the Slack. I think, if you let's be right together back in 3 minutes. Oh, okay. I think people are gathering in the main room as we speak. So, final thoughts.
I guess regarding avoiding biases, we cannot avoid them. And I think we should just do our best to understand what our biases are so that we could simulate our observations and understand what we should be expecting from our data. That's pretty much it. I mean, there's literally no way to avoid any sort of biases. That's my thought. Please correct me if I'm wrong.
I totally agree. I'm biased.
Yeah, selection effects for FRBs as a population. I guess we are limited, or luminosity limited, even at the current situation. Like we can only follow up sources that we could get imaging and redshifts for. So that is definitely, I guess that's what shows in the McCart plot. You're seeing higher and higher DM host as a result. Could be something to investigate. And how to obtain the number of host galaxies? What is the number? That's the question.
Yeah, I think we people are gathering. Thank you, Sunil. People are coming back to the main room.
Okay, everybody, let's discuss as a group. Hi, welcome back.
Okay, so hopefully everybody, can you guys hear me in the back? Yes. Okay, hopefully everyone's discussions went well. So now we're gonna have each of the discussion groups report back on some of the key points. So hopefully you have someone who will be reporting back from your group. And I think to start, let's actually start with the online folks.
Okay, thank you for choosing us. Okay, yeah, we were discussing many topics, different topics, but I think we ended up more or less with what we put there as a final summary plot. So yeah, I don't have it here. So yeah, biases are unavoidable. So we don't try to correct for them in a priori, but just design an experiment in which we know the bias as much as we can, and then we correct them accordingly for the interpretation, and then we do a different experiment with different set of biases. The selection effects, and Sunil, do you want to comment more on that? I think you have a very interesting thought on that.
Yeah, I guess one thing I was thinking about is that we are currently selecting optically bright FRB hosts. So basically, we would have to have detected the host in imaging to have even or like followed up that host, and then we should have gotten spectroscopic redshifts for them to do any sort of analysis. So at the moment, I think we can sort of see this effect in the McCart plot that I showed, where as you go towards higher and higher redshift, it appears that the mean dispersion measure of the host seems to be increasing. And this could be entirely because of the fact that we're just selecting for more massive galaxies as we go further out. So this is something to keep in mind, and this will affect pretty much any analysis unless we specifically design an experiment. So in the case of, say, dwarf galaxies or dwarf host populations, where we make sure that we drill down, I don't know, 6 hours at a time for a particular source, just to get imaging and make sure that we are complete down to whatever depth that we designed the experiment for. And I think, yeah, we would have to deal with it that way.
And then the final question is about, yeah, how do we get the required numbers? And that question depends on the yeah, it's too open. So will totally depend on the question, the science question you want to answer. We'll leave it at that. I think, sorry, Tarani, for interrupting. Online people, we are not listening to you. Yes. Okay, thanks.
Sorry, yeah, I was just asking for questions or comments on any of that from anyone in the audience. Okay, if not, I'm gonna pick on Tomas since. Okay, thank you guys.
Hey, hello, I'm Tomás from Universidad de Chile, and I am a comments that we gathered so far. There's been lots of discussion on many topics we try to gather here, but there, for example, the fact that how do we deal on following up a few sources? Let's say one of us found a high DM, 2000 DM FRB and well localized. We want to follow it up right away, right? So how do we first convince our audience that we want to observe that? There's many other projects going around, particularly in optical. So we sort of came up with a conclusion that it's best to join forces in things like this, in the community, especially since we are a small community of FRB enthusiasts. It would be good to join forces in at the time of following up multiple sources. Also, the questions of what to actually look at, it varies, as Nicolas was saying, with the actual science that you want to target. So we were saying as well, let's have then our own instrument to have our own set of rules in what do we want to observe. Let's say we have a 10-meter telescope in the north and one in the south, and then we observe just FRBs to follow up them with a spectroscopic redshift. So, but then again comes the question, so what type of science you want to do, right? Will that, that'll dominate the question back again. Some of the things that I got was, well, there's also like not only biases by our what we want to observe on the science itself, but also like academic biases as well when we want to, I don't know, promote the career of a scientist in early stages, right? So we also need to take into account that consideration. Anyway, so in summary, there will be many of these biases that we need to acknowledge, and as the people were saying before, it is hard to abstract ourselves from them, but we need to acknowledge them and try to incorporate them in the analysis rather than in the process of implementing these observations. I don't know if I'm missing something else here from our group.
Any questions, thoughts?
I had a comment on that. So obviously it will not be possible for us to build our own 10-meter class telescope, but what we could do, and I guess Tarne knows best about this, is to try to get a large program grant, which will allow us to have a dedicated amount of time every semester to follow up our target. So if as a community we could come together and decide on science cases that could be interesting on a large scale, say 3 to 5 years time scale, we could then pull together our resources and request, say, a Gemini LLP, for instance, where we got, say, 200 hours in total over the span of 3 years to do this particular science. So maybe we should be starting to think about those sort of science cases.
Yeah, are there any thoughts on coordinated efforts across FRB collaborations? I feel like surely there are. Okay, well, no takers for now. So can we get a representative from the upper half of the auditorium group?
Okay, so this is Casey. I was the first one to speak in the upper hall. So I am now the designated representative. I think it's fairly consistent with other summaries I've heard. I think there was one point we made, which was that it's good to distinguish the biggest problem statement from like the actual detailed science questions you want to ask. So if you're just saying, how do we measure redshifts for all the FRBs, it's a lot harder than if you say like, well, how do you, how do you find the peculiar persistent counterpart, or dwarf galaxy hosts, or how do you do the cosmology, precision cosmology applications? So, distinguishing that way means that in many cases, the problem is solved by other large survey programs. Euclid or what have you. I think there is, right now we're in the domain of really chasing every FRB down as best we can. And so we're sort of had this prejudice towards like spending lots of resources to maintain that in the future. I think that might be a failing effort eventually. So that's one possibility you should consider, is just maybe you get 90% of them and you're okay, right? But that's sensitive to your science goal, your science questions. But then if you do want to chase down all of the oddballs and get every last one, then an example was raised in our group of European collaborations which have coordinated around mega proposals for follow-up. And so that's been successful for GRB follow-up in particular. So that's one thing that we should consider in the FRB community as well. Let's see, what else did we say? Did I forget anything? Teammates. I guess that's it. I'll stop there.
Okay, any comments or responses? Yeah.
It's Ilya Hrichin here. Just a quick thought to follow up on everything, I guess. I think we should realize that we are not the first astronomers in the history of humankind that are facing this problem. Whenever the new class of objects is discovered, first it starts as a small field, but then it grows. So I think it would be beneficial if we find examples. The first one that comes to mind is quasars. It started as a small field and then grew into dedicated surveys. So we should learn from past experiences. It will make our lives much easier.
Yeah, that's a great point. Other transient communities have definitely dealt with similar issues.
Yeah, so as someone who's in the GRB community, I can maybe somewhat speak on that behalf. In terms of the number of gamma ray burst host galaxies that are redshift measurements are needed for, it is a far, far lower number than what you guys are looking to be detecting, right? So in the GRB community, if you include Einstein probe transients as well, we're looking at maybe one a day. That's maybe half an hour of VLT time a night. And the whole of the GRB community work together to get this time. So I think in terms of learning from other communities, if that's the scale you want to go for, this totally works for us. It's fantastic. Like the way that the Stargate collaboration have worked is they've made, they post every single redshift they measure on a GCN, and it's fantastic. But I think if you want to go for more galaxies, certainly in the future, as it sounds like what you're going to get like 10 to the 4 FRBs a year or something, which is just wild. I don't think that will work in the same way as it's done for GRBs. Yeah, that's my 2 cents. Also true. Yeah. Who wants it next?
Okay, maybe we should go to the second floor representative. Who is that? Adam.
Oh, okay, wait. Oh, no. Alex, can I pass it to you? And you just pass it along. I don't know who to pass it to. Oh my God, I can't throw
Nice.
All right, for folks online, I'm Adam Lamb, I'm Jeff from MIT. I haven't gotten to talk on this yet. It's kind of neat. I guess the main thing that we mostly focused on biases and try to come up with our own list of biases that we understood to be present in the data. The major theme of that was related to path and how one of the potential biases that we're starting to see more associations of FRBs with globular clusters or dwarf or satellite galaxies or things that are not directly related to the immediate galaxies. So relying on path associations could mean that we miss out on more or get the wrong sense of what the host galaxy population is if that's a major trend in the data. There was also a question about if you, I guess, did write some things down and took a picture of the notes. Yeah, if you're looking at local environment studies, you have the same angular area, but different distances are going to be biased toward nearby hosts for that. And yeah, then if you're relying on a probability of association from path as your cutoff, then your subsample within that, that's going to be if that's your sample for follow-up for local environments, then you're also avoiding the population of satellite galaxies and things potentially. There was also the discussion of using path associations to prioritize spec-C follow-up on certain things. Like if you don't get a confident host association, and then you decide, well, those are the ones we're going to follow up on, that can potentially introduce a new bias too, where we no longer have a uniform sample. So I think takeaway from that is doing these kinds of analyses, or ideally you would have a follow-up strategy that doesn't rely on properties of the burst, that you just say like everything within this range of properties we will follow up on. Of course, that then faces against the logistical challenge of having to have a uniform sample that you've done follow up on for everything, and that's not really practical. So I think it sounds like this some of these the strategy from the GRB community might be useful for that. But yeah, am I missing anything from that room? Or?
Any comments or questions on any of that? Okay, if we can get, thank you, Adam. If we can get a third floor representative, please.
Right. Thanks, Matt. All right. So our conversation actually kind of tried to look into more of the application aspects. Like, we need to select the sources in a way that how we are interested in it. For example, when we go high redshift, we look for how we can use it for cosmology and lenses that we have in the larger perspective, like, strong lensing. For example, the chances of having strong lensing or lensing from CGM and everything are higher when you go to high redshift, because you need the chances that you encounter such sight lines are only probabilistically higher as you go to high redshift. So that's one class that we have. The second class is the low redshift sources, where stellar mass lenses are and stuff like that are also. I think I'm maybe adding a point to it. Maybe plasma lenses are quite interesting at low redshifts, where you can reliably get the scattering and scintillations, and we're reliable. It's quite reliable based on the number of screens that we might be encountering as well. So the complication associated with that. We had a long discussion based on Matt's talk on FRB timing and how actually we can use. We had a lot of term about we talked a lot about precision cosmology over there. The chances that we would be able to do that, and the complications that we might encounter, especially based on Zarif's work on coherent lensing, search for coherent lensing in CHIME catalog, and how coherence could be lost, and how to find such sources where you have coherence in the voltage data, and use target such sources so that you actually look at these sources based on the redshift ranges. Yeah, and maybe is there anything else you need to add?
That was great. Yeah, so for each of these science cases, we broke them down into things that were just small little itty bitty numbers of events. You have something that you've observed lensing in, you're going to follow it up. We have the resources to do that. You have the highest redshift FRB you've ever seen, we're going to follow it up to the best of our ability, and so forth. And then there's separate from that all those science cases that need large statistics. And that's going to be potentially the hard part, but also the place where the lone prophecy, sorry, I'm pointing at his hair that he was right here. Be optimistic. Really what you have to evaluate is what error on the redshift you need for that science, which we thought we couldn't come up with a great example where the error would be smaller than the photometric error. And separate from that, what the penalty you pay in systematics is when there's a small number of your events that are horribly wrong, right? So in our photometric follow-up, what we typically get is an error bar when we get the right association, and it's bigger than the spectroscopic one, and you pay a price, and that's just easy to simulate and put through your science. And then on the other hand, for a bunch of the events, 1% of them, 5% of them, you just get the wrong answer entirely, and you have to figure out whether your science cares about that. Finally, if your statistics are high, you can do your science in the region where you have free follow-up at some redshift from existing efforts in that region where you don't. And you can compare, you can jackknife between them. So the lone prophecy. Oh, and we also have the McQuinn curse, which is that cosmology is hard, which we'll see if that's followed up. And we discovered, the chairs everywhere in this building so far are chiral.
Okay, thank you.
Yeah.
Any thoughts from anyone in the room, anyone online?
Just a quick thought on that. I think it's also important to know that for some use cases, it's not just the redshift that we would need. We'd also need if you're trying to look at local environments or trying to characterize the local the properties of the local environment, you might need more information either from imaging or spectroscopy. So characterizing the error bars that you need on those other parameters would also be very important.
You think that ever falls in a not small number count?
I think so, yeah, because if you are trying to understand the, if FRBs, for example, are all coming from, just taking, random example, but are all coming from star forming regions or highly dense, extremely dense or turbulent regions, then you need a large sample to see if they're, all coming from, if they all have variable RMs or all have, a certain, if you can localize them to a star forming region or something, but just getting the few use cases, the few examples is not going to tell you if all FRBs follow that trend. Yeah, at least that's how I was thinking about it.
Yeah, I totally agree with that. And I think another example is repeaters versus non-repeaters. Repeaters are such a small fraction of hosts right now. But overrepresented, yeah. Okay, so I know we're way over time. So I think we should wrap up. A common theme that I kind of heard across all of these is that your science really is kind of driving, your sample selection, your biases.
We have one more group that we forgot. We just do it really quick, the lobby, and then also right after.
Never mind.
Is there a lobby? Oh, good. Of course, on the other side of the room.
Okay, sorry, I'll keep this really brief. First, shout out to Alice for taking the notes that I'm partially relying on. Okay, Just a couple of very brief points that I think have not come up already. First is that, it doesn't seem like we fully understand the selection biases in our host association methods right now. I mean, Adam mentioned Bridget Anderson's work, which is a really great example of, trying to develop methods to do that. But one other example is that it doesn't seem like we have a good published sense of how many hostless FRBs there are right now that are not being followed up because we're not seeing evidence of a host in initial imaging. And then the other thing we talked a lot about was the need for dedicated follow-up of high redshift sources. This is one obvious example of a subset of FRBs where, dedicated surveys that are already planned will not be sufficient. One issue, though, is that it doesn't seem obvious whether FRB surveys are actually optimized for high redshift sources right now. Why aren't we detecting more high redshift FRBs already? So that just seems like an open issue. And then just broadly in terms of temperature of the room, it seemed like we were largely agreeing with Calvin. Oh, sorry, not this room, our discussion out there. Yes.
Thank you. Any comments, thoughts? Okay. So thank you, everybody. I think that was a really nice discussion. A lot of common themes, a lot of things to think about in terms of, how and if the FRB community wants to come together to pursue certain things, proposals, etc. Also just thinking about how to take advantage of publicly available surveys that will make a big difference for some science cases, but keeping in mind that other science cases will need more than just what we kind of get for free from a lot of these surveys. Nicolas, did you want to add any final thoughts?
No, I think several topics were covered, and it's good also to have different perspectives and prospects of how this science will move forward. So I think it was a very great and enlightening discussion. So thank you. And I disagree with.
Okay. Oh, sorry. I was just going to say, can we have a round of applause for Taryn and Nicholas? And then before we send you off, just one quick announcement from Matt Dobbs.
Great. So tomorrow afternoon after the conference, everyone's invited up to see the labs on the second floor of the Rutherford building. So to get up there, you just walk straight uphill until you see the TSI building and the Rutherford building. You can choose to go into TSI and hang out there, see the room where it all happened, or you can come up to the labs there. We're going to have a tour of 2 labs. They're not huge enough for everyone to go in at the same time. So it's just kind of a walk-through thing. There's our radio lab where we develop the custom electronics for the correlator of chime, how it digitizes the data, how it does the signal processing before it sends it out to the computer clusters. And you can talk to the folks there, people like Seth and others in the lab that will give you a bit of a tour. And then next door to that, there's the millimeter lab where we build superconducting detectors and readout systems for other science like the South Pole Telescope. So you can cycle through there and see that stuff. When you do, you'll see things like the first superconducting wafer from the Apex telescope. It's broken in half because someone dropped it in one of our tours, so be very careful and don't touch things. And if you're from McGill and you haven't toured the lab yet, you're totally welcome to come in. But if it looks crowded, just come back another day. And when you do, bring back those Phillips screwdrivers that you borrowed before and you haven't removed. We would love to not have to replace them at 10 per week. Finally, to add to the controversial statements, for getting back to on Friday when we talked about next generation telescopes, I'd like to assert that we are the most fortunate radio astronomers there are. And the reason for that is that we've already built a telescope that has essentially 0 sensitivity to intermittent local RFI. Cool, right? Yeah, the chime outriggers are any outrigger that's triggered over here and looks at the sky over here for short durations of times like transients, gets to look through all the RFI because it's not biased in what it detects, right? So we've already done it. We know how. And not only that, the Starlink satellites that are overhead for chime are different from the ones that are overhead for the outriggers. So we don't even care about Starlink. It's not going to kill our future. We are the only radio astronomers with a future on planet Earth. And we've already We've already done it, except we've missed the last step. If we just, next time we build a telescope like Cord, if we just build 2 of them in very different areas, full size, instead of just having our outrigger being not sensitive, then this telescope can see the sky through its own selection. That telescope can see the sky. And our limit on everything in our signal to noise is that RFI. If we require instead that one telescope sees the event, but both of them see it in different RFI environments, in our trigger, we will also not have sensitivity to RFI. This all comes at just a cost of maybe 50% more because half our budget goes to people and software. If we only had 50% more, we could be insensitive to RFI in our future. And on top of that, it's like going to Costco because while you have to buy more, the cost per item per FRB is so much cheaper because you can lower the threshold. So yeah, we should. Sorry? And with 3. And there's a coupon available where you can save even more if you spend more, just like air miles. So
Thanks, Matt. Let's talk more over dinner and on Friday.